afternoon, everyone. Thank you, Purushottam. Here's wishing Professor Balu a very happy 70th birthday. 5 years ago, we had two big celebrations to celebrate his 65th in two different cities in India. But this time it looks we have an even more massive celebration with so many people across so many continents and countries joining in. So today I want to talk about some recent joint work with Shantanu Prasad Bernwal and Mathukumali Vidyasagar. Very specific interest in the theory of Ramanujan graphs and bigraphs because of some very interesting applications that these types of graphs and bigraphs have in engineering. So I'd like to talk about this work. So we will go along at a leisurely pace. We'll first start with some basic aspects of graph theory, introduce definition of Ramanujan graphs and bigraphs, and try and understand why they are so important in number theory. And we will then move on to certain very nice and explicit constructions of what are called unbalanced Ramanujan graphs and try and understand the use of these bigraphs from the point of view of applications as well. So a graph consists of a vertex set V and an edge set E, which is contained in V cross V. So for any two vertices, Vi and Vj, we say if Vi comma Vj lies in the set E, we say that the vertices Vi and Vj are joined by an edge. And if Vi comma Vj lying in E also implies that Vj comma Vi lies in E, that is, if we don't worry about the orders, then the graph is said to be undirected. So we will be assuming that all the graphs in today's talk are actually undirected graphs. Okay, now these Vi and Vj are said to be the endpoints of an edge Vi comma Vj. And a loop is an edge with the same endpoints. We will further assume that the graphs in this talk are simple graphs, so they do not have any loops. Now, the degree of a vertex V refers to the number of vertices X such that X comma V lies in the edge set. And a graph is said to be a D-regular graph if every vertex in the graph has the same degree D. Now, a path in a graph is a sequence. So we are not just worried about edges now. We can have a sequence of edges moving across various vertices. So this is defined by the notion of a path. A path in a graph is a sequence of distinct vertices in the vertex set, except possibly V1 and Vk, such that Vi comma Vi plus 1 for each I lies in the edge set E. And if V1 is equal to Vk, then we say that this path is a cycle. And the length of a path is the number of edges in the path. Okay, now we have this notion of diameter of a graph. So as I mentioned before, henceforth, we consider finite, undirected, simple graphs. A graph is said to be connected if any two vertices in the vertex set can be joined by a path. And the distance between any two vertices, U and V, is the shortest length of a path joining them. There can be more than one path joining U and V. So the length of the shortest path is what is called the distance. And the diameter of a connected graph is the maximum distance between all pairs of vertices. Okay, so for example, let's take the most obvious example that comes, the most immediate example that comes to mind, namely the complete graph on n vertices. So this is a graph on n vertices such that there is an edge between any two vertices. And one can see immediately that this is an n minus 1 regular graph and it has diameter 1. Now a cycle C sub n on n vertices can also be interpreted as a 2 regular graph, and its diameter is the floor function of n over 2. The efficiency of the graph. So typically graph provide us with a mathematical model for situations where you have networks, so situations where you have different nodes and you have connections between uh, subsets of these nodes. And how do we judge the efficiency of a graph? Suppose you have a graph with a very large number of vertices, but very few connections between them, meaning you have big clusters of vertices which are not joined by edges from other clusters. So those graphs will not be very helpful from an application point of view. So the other extreme situation is that you have a large number of vertices, but you also have a very, very large number of edges, for example, in the complete graph. But there, the problem is that of use of too many resources to ensure connectivity across all nodes. So to judge how efficient or how efficient a graph is, or what is the quality of a graph, one notion is to uh, understand the diameter. So if you have a graph with relatively small diameter in comparison to the number of vertices, that would be a good graph from network point of view. So this takes us towards the topic of Ramanujan graphs in the following way. So there's a very famous 1989 theorem of Fan Chung, which provides a bound for the diameter of a connected d-regular graph in terms of a quantity called the spectral gap of the graph, which in turn depends on eigenvalues of the graph. So let's go over that notion. So suppose we label the vertices of a finite graph as v1, v2 up till v sub n. We can define what is called its adjacency matrix as an n by n matrix in which the ijth entry is 1 if vi comma vj lies in the edge set of the graph and it is 0 otherwise. Okay, so since X is an undirected graph, we immediately see that the adjacency matrix is symmetric and therefore it only has real eigenvalues. These eigenvalues are called the eigenvalues of the graph. Now, some eigenvalues can be deciphered immediately from the information given to us. For example, if X is a d-regular graph, then you can immediately see that your D, because the row sums of all the rows in A is D, one can see that D itself, which is the degree of regularity, is an eigenvalue of A, and this is usually referred to as the trivial eigenvalue. Moreover, by some more work, one can also show that for any eigenvalue of capital X, the absolute value of the eigenvalue is bounded above by D. So in particular, we have the notion of a spectral radius, which is the maximum of the absolute values of all the eigenvalues of the graph. And in this case, we know that the spectral radius is bounded above by D. In fact, since D is an eigenvalue, the spectral radius is exactly equal to D if you have a D-regular graph. So now we in 1995. And you will observe from all these inequalities that to minimize the diameter, we need to minimize lambda of x. So in this connection, there's a very famous theorem of Allen and Bopana in 1986, which says the following. Suppose you take some number d, positive number d, and fix it, and you consider d regular graphs on n vertices, then as n goes to infinity, then the limit infimum of lambda of x sub n is greater than or equal to 2 times square root of d minus 1. And in particular, a d-regular graph x is said to be a Ramanujan graph if lambda of x is less than or equal to 2 times square root of d minus 1. So this represents the optimal situation with respect to lambda of x derived from the Allen-Bopana bound. Okay, in other words, in a Ramanujan graph, all the non-trivial eigenvalues lie in the interval minus 2 times square root of d minus 1, comma 2 times square root of d minus 1. Okay, now we move to some very special graphs, namely bipartite graphs. So a graph is said to be bipartite if you can partition the vertex set of V into two sets, VR and V sub C, such that the vertices in each of the sets, VR and VC, among themselves are not connected to each other. So there is no edge between any two vertices in VR or any two vertices in VC. So for any edge in this graph, the edge must join a vertex in VR to a vertex in VC. A bipartite graph is said to be balanced if VR and VC have the same cardinality and unbalanced otherwise. A bipartite graph, furthermore, is said to be dr-dc biregular. So when we were talking about d-regular graphs, we have to specify a degree. Here we specify, so we are talking about a larger class of graphs now. So we say that a bipartite graph is said to be dr-dc biregular. Which I'll now explain. So first of all, as I mentioned before, the multiplicity of the degree d as an eigenvalue of a d-regular graph equals the number of connected components of the graph. A connected d-regular graph is a bipartite graph if and only if minus d is also an eigenvalue of the graph. And something very special happens in bipartite graphs. The spectrum, namely the eigenvalues of the graph, turn out to be symmetric about the origin. So if lambda is an eigenvalue, then minus lambda will also be an eigenvalue of a bipartite graph. Okay, so now when we have a bipartite biregular graph with degrees dr and dc, then in the adjacency matrix, there will be large blocks which will just contain the entry 0. So the really relevant part of the adjacency matrix is what we call the bi-adjacency matrix, where the rows are labeled by the vertices of VR and the columns are labeled by the vertices of VC. And the entries 0 and 1 appear as per whether a certain vertex is connected to a vertex in the other set or not. But now, obviously, in many situations, capital B need not be a square matrix anymore. So that's why we can talk about singular values of these rectangular matrices B. So in particular, in a DRDC biregular graph, square root of DRDC is the largest singular value of the biadjacency matrix B. And in case you have not heard the definition of singular values, it simply refers to the square roots of the non-negative eigenvalues of B transpose of B. Okay. So the relation between eigenvalues of the adjacency matrix and the singular values of the biadjacency matrix can also be written out clearly. So the eigenvalues of A equal plus or minus sigma sub I, where there are L many sigma i's, L being the minimum of the cardinalities of VR and VC, and sigma 1, sigma 2 up till sigma L are the singular values of B. Okay, and there are also certain number of zeros which will show up. So zeros, zero with a certain multiplicity will show up as an eigenvalue of A. We now denote analogously to the notion for eigenvalues of graphs. We can talk about bipartite, biregular graph, and we can talk about sigma of x, which we denote as the maximum of the absolute values of the biadjacency matrices, of the biadjacency matrix, which are not equal to the trivial, the so-called trivial singular value. Okay. And as an extension of Allen-Bopana theorem to this setting, suppose we take dr comma dc and we fix dr and dc, and we take a sequence of vertices, sequence of sizes of vertices nr and nc in such a way, of course, that dr nr has to be equal to dc times nc. So with this restriction, if your n sub r and n sub c tend to infinity, then the limit infimum of your sigma, okay, which is the analog of lambda here, is at least square root of dr minus 1 plus square root of dc minus 1. And in case you have a balanced Ramanujan, if you have a balanced bigraph, then of course this is it. We end up getting the same bound as from the Allen-Bopana theorem. Okay, so just as we had the notion of Ramanujan graphs, now in a very similar way, we can define the notion of Ramanujan bigraphs. So a DRDC, biregular, bipartite graph is said to be a Ramanujan bigraph if sigma is at most square root of dr minus 1 plus square root of dc minus 1. Note the following. Given a D-regular graph, we know that D is its largest eigenvalue. So a Ramanujan graph by definition is one for which the lambda, the ratio of lambda over lambda sub 1 is as small as possible, okay, in view of the Allen-Bopana bound. Similarly, when you have a DRDC regular bipartite graph, a Ramanujan bigraph is one in which the ratio of sigma over sigma sub 1 is as small as possible. This is in view of the Feingley bound. Now we come to questions about existence of Ramanujan graphs and bigraphs. So the basic question is, how pervasive are these graphs and bigraphs? So there's a very nice theorem of Friedman in 2003, which tells us the following. If you fix D and let your number of vertices n go to infinity, then the fraction of D regular n vertex graph that satisfy the Ramanujan property, it just keeps increasing and it comes closer and closer to 1. Similarly, in the setting of Ramanujan bigraphs, you have an analogous theorem proved by Brito, Dumitrio, and Harris in 2018. Here you fix dr and dc, and you let nr and nc go to infinity, subject, of course, to the bipartite condition. Then with this condition, the fraction of DRDC by regular graphs, which are Ramanujan, this fraction approach is 1. So this means that what these theorems tell us is that Ramanujan graphs and bigraphs are very pervasive. They are spread in nature around us. But despite their prevalence, uh, an interesting aspect, an intriguing aspect of these graphs is that there are relatively few explicit methods for constructing Ramanujan graphs and bigraphs. It is this here we should also recall one of the most celebrated theorems in recent times by Marcus Spielmann and Srivastava in 2015, which says that for any d greater than 2, there exist infinite families of d-regular bipartite Ramanujan graphs. So this again brings us back to the question of specific examples of Ramanujan graphs and bigraphs, and not just one or two examples. We'd like to construct large families of these graphs or bigraphs. So here are some questions. Given d greater than or equal to 3, can we construct explicitly a sequence of integers n sub I with n sub I going to infinity and a corresponding set of d-regular Ramanujan graphs with ni vertices? Similarly, given fixed degrees dr/dc, can we construct explicitly a sequence of integer pairs nr/nc and a corresponding set of Ramanujan bigraphs with nr/nc vertices? Now, in the previous two questions, we were fixing the degree. Now we ask a slightly different question. Is it possible to permit d itself, or dr/dc more generally, itself to increase to infinity in the case of Ramanujan graphs or Ramanujan bigraphs as nr and nc keep increasing? So now in the context of Ramanujan graphs, there are some explicit constructions, and these constructions are very closely related to extremely important theorems in number theory and representation theory. So one of the earliest constructions of Ramanujan graphs is the famous construction of Lubotsky, Phillips, and Sarnak in 1988. So they constructed an explicit family of d-regular n-vertex Ramanujan graphs where d is equal to p plus 1 and n is equal to q times q square minus 1, where here p and q are both prime numbers congruent to 1 mod 4. I'll make some more comments about this construction shortly, but notice here what we can have is we can actually fix a prime p congruent to 1 mod 4. So we have a fixed d, and we can have a sequence of primes q which are congruent to 1 mod 4 going towards infinity. And so this way we have an explicit family of Ramanujan graphs with increasing size of vertices. At the same time, Margulis also had an explicit construction of an infinite family of Ramanujan graphs with exactly the same parameters as above. And in 1992, Winnie Lee described graphs that would conform to the third question that we just asked. So here you've got Ramanujan graphs of degree d equal to q plus 1, and the vertex size is either q square plus q plus 1, or certain other expressions involving degree of these graphs. Then there's another example by Morgenstern in 1994, where he constructed an infinite family of d-regular Ramanujan graphs with d equal to p to the a plus 1 for any prime p and any a greater than or equal to 1. Now, there are some other constructions of Ramanujan graphs as well, but the reason I have written these, I'm just going to discuss these four, is that essentially they we have to use character sum estimates coming from the Ramanujan Deligne bound from the theory of modular forms. So this is a reason why the Ramanujan graphs are actually named after Ramanujan. Okay, now some thoughts about Winnie-Lee's construction. So suppose we have a finite field, okay, f sub q, where q is some prime power. And let us take f sub q square to be a degree 2 extension of f sub q. Here the generating set S is said to be the set of all primitive, is taken to be the set of all primitive elements of f sub q square. That is the set of all elements of multiplicative norm 1. Now S is symmetric and it contains q plus 1 elements.
Front, right. Front, right.
Evra and Parzanchevsky in 2018 also have some abstract constructions of infinite families of Ramanujan bigraphs with degrees p plus 1 and pq plus 1, but here their primes are congruent to 3 mod 4. For each suitable choice of p, the work of these authors, leads to an infinite family of Ramanujan bigraphs. However, at present, these constructions are not explicit in terms of resulting in a bi-adjacency matrix of zeros and ones. The authors have, we interacted with some of the authors, and we have been informed that they are working, trying to make these abstract constructions explicit is currently work in progress. Okay, so let me also recall here again another result of Marcus, Spielman, and Srivastava, which says that given any C comma D, we have an infinite family of Ramanujan C comma D bigraphs. Okay. So this brings us to the main content of the work that I'm going to report on today. So this is recent joint work with Shantanu Prasad Bernwal and Professor M. Vidyasagar. It is to appear in the Ramanujan Journal, and all the results that I'm going to talk about today form a part of Shantanu's PhD thesis. So to begin with, here are certain families of Ramanujan bigraphs for which we have very explicit constructions. And by explicit, we mean we can actually immediately construct we know exactly what the bi-adjacency matrix looks like. So the parameters here are LQ times LQ comma Q square, where Q is a prime power and L is a positive integer between 2 and Q. Sorry, not prime power, prime number. That's extremely important. I'll let you know why. On a related note, we also have Q square comma LQ bigraphs, where again Q is a prime and L is any integer greater than Q. In particular, if we take in the first instance, if we take L equal to Q, we are able to generate a new class of Ramanujan graphs, which does not match any of the known examples of Ramanujan graphs. And there is one contrast here in comparison with the previous constructions of Ballantine et al. That I talked about. Given a pair of integers L comma Q, we can construct only one Ramanujan bigraph. Okay, so let's just go over the method of construction of these unbalanced Ramanujan bigraphs. The method is really simple, very elementary, and it gives us an explicit bi-adjacency matrix immediately. In fact, the graphs are constructed by assigning something which turns out to be a valid bi-adjacency matrix. So here's what we do. We take a prime number Q and we let P to be a Q by Q square matrix. In fact, let P denote the cyclic shift permutation matrix. So what are the entries of P? If J is congruent to I minus 1 mod Q, then P sub I J is equal to 1, and it is 0 otherwise. So the matrix P is simply a shift of the identity matrix. You can take the identity matrix, shift the first row to the bottom of the matrix, and then raise the other rows by one row above. So that is basically the matrix that we are talking about. And we note immediately that the transpose of the cyclic shift matrix is exactly equal to its inverse. Another important fact is that if you take this matrix P and raise it to the power Q, you end up getting identity. So if K is congruent to L mod Q, then P to the K is equal to P to the L. Okay, now here is a nice fact which uses the primality of Q. So suppose we have all possible residues modulo Q, and K is a non-zero integer with absolute K less than Q. So it is, in other words, it is a non-zero residue class mod Q. Then as S runs over all the residue classes mod Q, so does K times S. And therefore, because of the previous equality, we immediately see that if we take P raised to the Ks and sum from S going from 0 to Q minus 1, This turns out to be equal to sum of p to the s, as s runs from 0 to q minus 1. And this turns out to be equal to that q by q matrix in which all entries are exactly equal to 1. Okay. Now what we do is we define the array code, what's called the array code q square by LQ matrix. It comes from the theory of error correcting codes. So we have this matrix C of q comma L, okay, which we define as combinations of blocks coming from P and its various powers. So it's sort of reminiscent of the van der Waals matrix. So what we now do is, so this turns out to be the way we've defined it. This is a q square by LQ matrix. And we can define the bi-adjacency matrix of a biregular graph, call it B, and this B is equal to C transpose if L lies between 2 and Q. And on the other hand, if we are taking L to be something greater than Q, then we just take the matrix C. With this in place, the first theorem is that, so we take L to lie between 2 and Q. So that's the first case. And let B, as we constructed previously, so in this case it is C transpose, let it represent the bi-adjacency matrix of an LQ comma Q square biregular graph. It turns out, it can be shown by some work, that it has a simple singular value of root QL that is known. And all the singular values other than root QL are just root Q with a multiplicity of L times Q minus 1 and 0 with the multiplicity of L minus 1. And therefore, B represents the bi-adjacency matrix of a Ramanujan bigraph. Okay, so a brief idea of proof. So what we have to do is we have to find out what are the singular values of B. So we take the matrix B transpose B, which is by the definition of the way we defined it is just C times C transpose of the matrix C. And we use a block partition to sort of divide this matrix into more appropriate blocks of smaller sizes. And it turns out that if you take any I and j lying between 0 and L minus 1, remember here L was less than or equal to Q, so L minus 1 is strictly less than Q. If you take the ijth, so C times C transpose sub I comma j is that matrix block which can be composed with the help of the following formula. So you have to take the ith row block of P and the jth column block of P transpose. And very nicely, very conveniently, using the fact that P transpose is P inverse, this just turns out to be P raised to the I minus j times S, where S runs over 0 and 0 to Q minus 1, all the residue classes mod Q. Now I minus j, since I and j lies between 0 and L minus 1, absolute of I minus j is strictly less than Q. And if in particular, if I is not equal to j, then from the fact that Q is a prime, we end up getting that the sum of P raised to the I minus j times S, as S varies from 0 to Q minus 1, just turns out to be that Q by Q matrix, all of whose entries are exactly equal to 1. And when I is equal to j, this matrix just turns out to be Q times the identity over Q, identity square matrix. So then with some more work, so this is the crucial place where we use the fact that Q is prime, and with some more analysis, we are able to derive all the singular values that I mentioned in the theorem. Okay. The other theorem relates to when L is greater than Q. So here we don't have the analysis here is not as comfortable as in the previous case, because your L is greater than Q. Here, since your L was strictly less than Q, you had this matrix sum identity. So here we have to divide the study into two smaller cases. either when L is 0 mod Q or when L is not equal to 0 mod Q. So there are different singular values that show up in these cases. However, all of them end up satisfying the Ramanujan condition. So this is also another example, a very explicit example of an unbalanced Ramanujan bigraph. Okay. And as I mentioned before, when we take L to be equal to Q, the previous theorem leads to the following corollary. We end up getting the biadjacency matrix of a Q square comma Q square bipartite balanced Ramanujan graph with degree Q. Okay. So here in this case, your eigenvalues turn out to be Q and square root of Q with a multiplicity of Q times Q minus 1. And the remaining Q minus 1 eigenvalues are 0. Okay. So now there's another aspect in the few minutes that remain that I'd like to comment on another aspect of our work, namely that if we have a Ramanujan bigraph, can we perturb the edges of the bigraph in such a way that after perturbation, you still retain the Ramanujan property of the perturbed bigraph? So there is, now this is a good time to understand the motivation behind these explicit constructions. So this work was carried out by Bernwal and Vidyasagar. So it relates to the matrix completion problem in engineering. So suppose you have a matrix, okay, of size nr by nc, which is unknown other than a known upper bound R on the rank of the matrix. And let us say we have a small subset of the entries for which we know what the values are. So we call this a sample set. And suppose we can measure entries in the sample set using what we know about the sample set as well as the bound on the rank of a matrix. Is it possible to determine the unknown matrix X completely and exactly? This is the matrix completion problem. And Bernwal and Vidyasagar have pursued this line of inquiry using Ramanujan graphs, and they have shown that if the sample set omega is chosen in a deterministic way as the edge set of a Ramanujan bigraph, then the answer to this question is, in fact, yes. Okay. Now, this leads to another question. In the kind of applications that they are interested in, the sample set that we know needs to be disjoint from a certain set, M, which we call the prohibited edges. So let me explain this clearly now. Suppose we are given vertex sets, VR and VC, where the cardinality of VR need not necessarily equal the cardinality of VC. And as before, I'm just repeating notation from before, these have cardinalities NR and NC. We are also given the degrees DR, DC. Moreover, we are given a set M contained in VR cross VC, which is called the set of prohibited edges. So our objective is to construct a DRDC bipartite Ramanujan graph such that the edge set of this bipartite Ramanujan graph is disjoint from the set of prohibited edges that we have chosen, the prohibited set M. And from the point of view of applications, we don't need M to be very big. M usually has small cardinality. So we'll make this more explicit shortly. So let's continue discussing perturbing a Ramanujan bigraph. So as before, we consider a DRDC biregular Ramanujan bigraph with a given biadjacency matrix, and let omega be its edge set, whereas let M be the set of S many prohibited edges. So what we are asking is if we can perturb the biadjacency matrix E in such a manner that the corresponding graph does not have any edges from the set M, which you have already fixed, And it is still a DRDC by regular Ramanujan bigraph. So even after perturbations, not only does it manage to save the bipartite property, but also the Ramanujan property. So in this connection, we also have the following theorem. Suppose E is the biadjacency matrix of a DRDC by regular Ramanujan graph. Let us define mu of dr comma dc as this optimal value of the non-trivial singular values. So square root of dr minus 1 plus square root of dc minus 1 coming from the Fengli bounds. So let sigma 2 denote the second largest singular value of E. So in a Ramanujan bigraph, we know that sigma 2 has to be bounded above by mu of dr comma dc. What we are interested in is the difference between this expected bound and the actual second largest singular value. So suppose we have an integer p, positive integer p, such that 2 times p is at most mu minus the second largest singular value. And suppose we have the following restrictions on the set M, namely M does not contain more than p values of j. So for any fixed I in the vertex set VR, there are at most j many elements, vertices in n sub c, so that ij lies in the set of prohibited edges. And the same thing happens in the reverse direction for every fixed j in the vertex set v sub c. So if this p, so suppose we have such a p for this happens, and in addition, 2 times p is less than or equal to mu minus the second largest singular value, then we can construct a DRDC by regular Ramanujan graph whose edge set is disjoint from the set of prohibited edges M. So what we can do is actually, when I don't have time to go over the proof, but briefly speaking, we start with a bipartite, we start with a Ramanujan bigraph, and then we perform some procedures to eliminate prohibited edges from them. So now before I conclude, some comments about the spectra of Ramanujan bigraphs. So you may have observed that the previous theorem shows that if the gap between the second largest singular value and the bound mu increases, then more perturbation is possible in your Ramanujan graph. However, we also learned the Allen-Bopana bounds and the Fengli bounds for bigraphs, which shows that as the graphs keep growing in size, the gap between mu and sigma 2 is in fact going to 0. So here the degrees remain fixed, right? For both these bounds in both the theorems of Allen-Bopana and Fengli, the degrees were fixed. Therefore, this does not pose a limitation to our scenario, because in the constructions that we presented, the degree of the bigraph increases along with the size of the graph. So your mu minus sigma 2 also keeps growing along with the degrees dr comma dc. Concluding remarks. So as I mentioned before, there are relatively few explicit constructions of Ramanujan graphs and balanced as well as unbalanced bigraphs. Here, we presented explicit constructions of an infinite family of unbalanced Ramanujan bigraphs, and this, we believe, is the first such explicit construction of a family of unbalanced Ramanujan bigraphs. So these explicit constructions are available for only certain combinations of degree and size, but it makes for a very good beginning. And it is known from the work of Marcus Spielman and Srivastava that Ramanujan graphs and bigraphs are known to exist for all degrees and all sizes. And therefore, this opens up it opens up an interesting field of inquiry about constructing unbalanced Ramanujan bigraphs for a variety of degrees and sizes. And Bernmal and Vidyasagar show that it is there's a very nice and useful application of Ramanujan bigraphs in uh, in engineering, and they show that it is in fact possible to guarantee the exact completion of an unknown matrix, provided the sample set that you already knew corresponds to the edge set of a Ramanujan bigraph. So I think I'll stop at this stage. Thank you.
Thank you, Kananika, for the beautiful talk. Anybody has any question or comments? Please go ahead. So just unmute yourself and ask. Sorry, so there is no restriction on L, right? L need not be, L can be any number, right? Q has to be prime.
Q has to be prime.
And L bigger than Q is the where it is a little bit more painful, a little bit.
Yeah, we have to be a little careful of whether it is 0 mod Q or not zero mod.
For L less than Q, you could break it into parts which are of at least length L, and because Q is prime, that helped you figure out this part. Whereas the other way is complicated because L is bigger than Q, so you have to read it mod Q, right?
Yes.
Sure.
Yeah.
Sure. Okay. If there is no more question, let's thank Kananika once again.
Thank you.
We have 5 minutes time. So. Sangha, can you upload your? Can you share your screen? I have made you the.
Yeah.
In fact, you are actually Professor B. Ramakrishnan. So. Try. Yeah, take your time. We have time.
Is it fine?
Yes, perfect. So we have 5 minutes. So
yeah, should I make it full screen?
I think it is. Isn't it full screen? It looks like full screen.
Oh, okay. Then it's fine.
So we have 5 more minutes. Okay.
Sure.
Sangha, you have a different title here. Which one I should use?
This one is better. Sorry.
No, it's okay. Why, sir? No, I suddenly realized that what I have here is different from what you have here.
Because I logged in as Ramki, I should give some theta function. So
I see.
no, just joking.
You can make it even more interesting. Linear independence of zeta value. So we will have
why did you log in as Ramki? Just like that.
No, he was not able to log in the beginning.
Oh, I see.
I had some trouble, so I just logged
in.
Where are you, in HRI or in Chennai? Where are you?
HRI only. HRI.
Yeah, his office I can see. You are going to Chennai tomorrow.
I cancelled it, sir.
Okay.
Because Anandi and Aruna, they were down with fever and cold. It may be possible that I will get it soon.
You were coming for campaigning, is it?
Yeah.
Sangha, did you have the vaccination?
No, I don't.
No, sir, not yet.
Oh, he cannot take it now.
Yes, sir.
What about you, sir? Sir, you have taken?
I have taken.
Oh, okay.
4 days back. First round. I will take it. You have after 28 days, the second dose also.
For me, I am in on a strong blood thinner now. So they say it will not work, neither of the vaccines.
Oh, you are on a blood thinner, I see.
Yeah.
Okay, sir. So we are now almost time. So it's my pleasure to introduce the last speaker of the session, Professor R. Thangadurai from Harishchandra Research Institute. He will be speaking on linear independence of special values of Jacobi theta constants. Thanga, go ahead.
Thank you. I'm thankful to the organizers for giving me opportunity to speak in this wonderful conference. I would like to convey my greetings to Balu sir on his birthday, 70th birthday. Okay, my title, though I gave different title, but this is the right title. The content is same, but title is different, that's all. So linear independence of special values of Jacobi theta constants. Sorry. Yeah. Okay, so the Jacobi theta constant is defined to be like, theta 3, it is generally called, and it is defined as the Fourier series. It is a half integral weight modular form with where Q, this is one of the most classical and well-studied object in number theory, being intimately connected to the study of integer partitions and representations of integers as sum of squares, half integral weight modular form, etc. The other Jacobi theta constants are defined as theta 2 and theta 4. It's just a variation of it. Theta 4 is just a variation of this, and theta 2 is another variant. So these three theta constants are...
Hey, Thanga, are you moving your slide or it's still there?
Yeah.
No, the slides are not moving at least.
Oh. Maybe I will...
Now it's moving.
Now it is okay?
Yeah.
Because I was in the full screen mode, so somehow it is not working.
No, ours was not moving. Sure.
Okay. So now it's clear. Okay, this theta 2, theta 3, theta 4, these are all periodic functions with period 2, where, okay, so we may not get into too much of modular form property, but very limited only. Okay, the study of transcendentance values of these theta constants and algebraic independence of values of these theta constants made a great progress after the celebrated theorem of Nestor and Co. in 1996, who studied the algebraic independence of normalized Eisenstein series. He calls it Ramanujan function, so I just mention it. Yeah, otherwise, it's a normalized Eisenstein series of weight 2, 4, and 6. He proved that for any complex number z, which is in non-zero complex number, which is inside the unit circle, at least one of the three numbers, three values of z are E2 of z or E4 of z or E6 of z. These are all, one of the three will be algebraically independent over Q. Okay, so this is, since it is a basic modular form, so I'm not just really defining. Using this algebraic independent result, and the connection between the modular form connection, the veteran in 1997 and independently other group, Nishioka and Shiwoka, in 97, they proved the following result in particular. So when we fix J 2, 3, 4 and tau in the upper plane H, assuming that e power I pi tau is algebraic, then the three functions are algebraically independent. What is the theta j of tau? The differential d of theta j of tau and d square of theta j of tau, where d is the differential operator by just multiplied by constant 1 by I pi. These three functions are algebraically independent over Q. Okay, whenever the tau is satisfying this condition, e power I pi tau is algebraic. Okay, so in particular, from this we can able to get the series n equal to 1 to infinity q n square is transcendental for any algebraic number q satisfying the inequality mod q is strictly less than 1 and it is non-zero. Okay, in 2018, Elsner and Tachia, they proved the following variant. There it is all but operator, the differential operator applied twice. Here they considered the following numbers, almost similar condition in on tau, but the three numbers are theta 3 tau, theta 3 n tau for given a integer n, and the d of theta 3 tau. These three are algebraically independent. In the same paper, they proved if you are taking if you are given three distinct integers L, M, N, then the tau in the upper plane, the three numbers theta 3 L tau, theta 3 M tau, theta 3 N tau, all are algebraically, these are all algebraically dependent. Okay, so this is though after applying the differential operator, that is algebraically independent, but here if we just take three distinct integers, they are algebraically dependent over Q. Okay, in 2019, Elsner, Luca, and Tachia, they proved that for any two, there it is three distinct integers, the theta values are algebraically dependent. Here for the same tau, no, for the same tau with tau is e power I pi tau is algebraic. For that, these two values of special values of this theta constant is algebraically independent over Q. Okay, so there, if we take three distinct integers, it's algebraically dependent, but two, if we take distinct integers, then the special value m tau and n tau gives produced algebraically independent. In 2019, Vikesh Kumar, he proved that for a special tau, it's a tau naught, which is like I log b by pi. The m and the m distinct values of m distinct integers satisfying some conditions saying that it is the quotient, any two quotient should not be perfect square in rational number. Okay, so if such a m integers are there, then this m theta values are q linearly independent. This is if you apply tau naught equal to I log b by pi in the theta value, what you get is usual BRI series. We will see that soon. This is part of his thesis. Later, recently, he proved along with Elsner that if we take m distinct integers, positive integers, the functions at the theta functions at these values a1 tau, am tau, as a function, it is c tau linearly independent as a functions. This is a recent work. Okay, in the same paper, they proved that among the other things, for any odd distinct positive integers m and n, if theta 3 tau, theta 3 m tau, theta 3 n tau, these are all q bar linearly independent. We already have seen that if we take three distinct integers, M, N, L, this is algebraically dependent, but still it can be Q bar linearly independent. In this particular case, they algebraic number of some degree greater than or equal to 3. Okay, this is the kind of brief history of what we are intended to prove in this talk. So before we state our main result, we need the following definition. Yeah, real number beta bigger than 1, a real number beta bigger than 1 is called a piezo-Vijayaraga number, or in short, a PV number of degree D, if beta is algebraic integer of degree D, and each Galois conjugate alpha not equal to beta, strictly, I mean, it lies inside the unit circle. Okay, then we call it PV number. This for every natural number m is a PV number of degree 1. For every d greater than or equal to 2, there are PV numbers of degree D. Okay, so there are infinitely many PV numbers. This has got much more properties. We are not going to tell. We are not going to enter that area, but we are going to use in this setup this particular PV number. Okay. Just we shall motivate towards our main result when we take tau as I log beta by pi for any real algebraic number beta bigger than 1. For any distinct integers m and n, the Elsner-Luca-Tachia result says that these two series are algebraically independent. Whereas if you take 3 distinct integers, these 3 series are algebraically dependent. Okay, so though they are algebraically dependent, 3 if you take, it is possible that they may be k linearly independent for a number field k. Of course, the main, I mean, the aim was q bar linearly independent, but it is still not going through. So at least k linearly independent for some number field k. So now we shall state our main result. This is a joint work with Devashish Karmakar and Vikesh Kumar. So let beta be the PV number, PV number, and m is greater than or equal to 2 any integer, and A1, A2, AM be the distinct positive integers, and we consider the m series of the same type along with 1. These m plus 1 things are q beta linearly independent. Okay, so of course because of the algebraic any two if you pick any 2 series, if you pick, it is algebraically independent. Therefore, in particular, every real number, every series, this values are transcendental already. And but what we are saying is that these are all q beta linearly independent. Okay, these are all transcendental numbers except one but it is these are all q beta linearly independent. So in the actually here I am just giving a proof for the numerator with numerator 1. One can take in the numerator, in the series, the numerator we can take a polynomial of polynomial growth functions we can put. But for the lecturing purpose, I am just taking a numerator to be 1. Okay, so we can deduce some of the corollaries, but the corollaries coming from once I take the polynomial, I mean the functions as a polynomial growth with the polynomial growth, then only then it will come. But just I'm just stating the corollaries one can obtain. The first one is kind of straightforward from the definition. Beta and A's are as above. And we take tau n to be I log beta by pi a plus 2n for any natural number n. Then we can say that the theta values, the special values of this theta 3 function are q beta linearly independent with 1. The next one is theta 4, the same result for theta 4. But this will come unless we take that previous result, instead of 1, we have to take some plus minus 1, fi to be plus minus 1 whole power I kind of. Then only then it will come. Otherwise, just for the sake of, I'm just stating. Similarly, the other corollaries. So one can mix up theta 2 and theta 4 together. One can get again q beta linearly independent with 1. The last one is B array expansion. B array expansion where CAs are digits, alphabets, or you collect. Okay, so this series also we can say that q linearly independent here, because here beta is nothing but a rational number, so therefore it is q linearly independent. Okay, so I will like to give the proof, but of course one case is this too much of computation. So at least first I will start with the idea of the proof, then I will check for two cases how the idea goes through. Okay, idea of the proof, suppose not, it means we want to prove this this m plus 1 values are q beta linearly independent. We assume that it is linearly dependent. It means there exists a constant C0, C1, Cm belongs to q beta. We can assume that it is all algebraic, they are all algebraic integers, and the linear combination of these numbers gives rise to 0. Okay, so for any m natural numbers, n1, n2, nm, we look at we just break this left hand side of partial sums, the linear combination of partial sums, and the rest tail. What we want is once you have this series linear relation is 0, then there should be partial sum, the same relation should vanish. Okay, that is the first, this is the main idea of this. Okay, so we want to choose n1, n2, nm in such a way that the left hand side of the above is 0. Okay, that's what it means. The second, we want to choose some n1, n2, nm. Okay, one way to do this, okay, if you look at this left hand side, one way to do this, these are all algebraic numbers now because there is a denominator is there. So if I clear out denominator somehow, then I can make it as an algebraic integer. That's what one way to do this. If we multiply both sides by beta power a1 n1 square, and we want this quantity xn1, just it is a multiplication of the left hand side of this intermediate step. Okay, so this is xn1. If all this powers, each summoned, the powers are greater than or equal to 0, then the xn1 is an algebraic integer in q beta. So this, because ni's are in our hand, so by choosing ni to be n1 square root of, because you see this I want to greater than or equal to 0, therefore just it's a natural choice that ni we choose to be the integral part of n1 times square root of a1 by ai for each I equal to 1, 2, 3, 4, etc. So with the assumption that of course a1 is the smallest and a2 is the second one, etc., and am is the largest. These are all positive integers only we have taken, undistinct. So this using the, once we choose these ni's like this, then xn1 is an algebraic integer. Okay, now we want this to make it to 0, then we compute the norm. If we can prove that the norm of xn1 is strictly less than 1 absolute value, then this is xn1 is 0. So in this way of choosing ni, then n1 becomes a parameter. N1 is in our hand, so we can choose as large as possible so that this norm becomes less than 1. So this is achieved. This norm, computing norm, this is less than 1 is achieved by using the fact that beta is a PV number, and one more relation, which is once you have chosen this ni is like this, then the other relation also more or less will come. This is the relation for any given r, natural number r, a times ni plus r whole square minus a1 n1 square. This is bigger than this. Okay. So from this way of choosing ni's and make sure that this relation holds, then we can make sure that once the linear combination of the series is 0, then there exists a partial sum of the same linear relation is 0. That's what the first step. Okay, this is case 1. This is here. This is okay. Suppose if a1 n1 square minus a ni square is at least, it's not only greater than or equal to 0, but also some power of n1, some small power of n1, then you see this is immediately we can get a result. Why? What we have is the relation 2. So once we have the relation 2 we have, from this relation, we just adjust. We bring the n minus n1th kind of, okay. So in the first sum, C1 times the first sum, in the top, the beta power a capital N1 square, you just remove, rest all you bring it to the right hand side. Okay. Then let rest all bring it to the right hand side and choose one R1, little r1, which is like roughly like n1 power some kappa 1, where kappa 1 is strictly less than kappa. That the kappa is coming from the lower bound of the relation NIS. So you just adjust so C1 by beta power R1 and the rest. This, if we can make sure, now you see there is a denominator in the inside the parenthesis, and we are multiplying by beta powers. Suppose after multiplying by beta powers, if we make sure that everything in the numerator, then again this is this is algebraic integer, and this is bounded above by, and this is an algebraic integer and bounded above by beta power minus R1. Okay, so this, we really make sure that in this case we can, this of course if we assume first condition, then this condition is obvious because we have chosen R1 to be something smaller than the lower bound what we had. So therefore we can able to make sure that this yn1 is 0. It means the right hand side is 0. It means that C1 should be 0. Okay, so what if we have this condition, then C1 is 0, the first coefficient. We want to prove all the coefficients are 0. Now once C1 is 0, now we are end up with m minus 1 series along with 1, and we can continue the same process if this case happens all the time. Okay, suppose the other case, if the relation just we know greater than or equal to 0, a1 n1 square minus a ni square greater than or equal to 0, but we don't know the better lower bound than 0. There is one case in this is exactly going to be 0. So therefore we have to follow this step for that particular case. Okay, in this case what we do, we just take out in the partial sum linear combination 0. From that we adjust only the n1 n2 nm, the term you just bring it to the right hand side, rest all you keep it in the left hand side. Okay, that is what the equation 3. Now we choose, we have already chosen R1, or it is in our hand. We choose in such a way that two relations happens. This is as of now it is like just hypothetical, but soon we will give a situation where we can able to choose like this. Okay, so this is first condition is really needed just to make sure that the same. So the first condition is make sure that this is a yn1 is an algebraic integer. Okay, so the second condition will make sure that something is yn1 bounded above by beta power 1 by beta power minus R1. Okay, so therefore these two, with this two, we can able to force yn1 0. So once you have, it means again, these are all, you see the NIs we are going to, we will have infinitely many NIs satisfying this kind of relations. So for large enough NIs, we can able to make sure that yn1 is 0. Okay, so once this left hand side is 0, this yn1 is 0, the left hand side is 0. Okay, so then again you adjust the the highest one, that is n1 minus 1th coefficient, n1 minus 1th term, you just bring it and keep it in the left hand side, and rest all you bring it to the right hand side. And because of the first condition, again the previous one, we can again make sure that this zn1, this is an algebraic integer, and because of the left hand side, this z1 is bounded above by beta power minus r1, and this two conditions, we can make sure that the norm of zn1 is strictly less than 1 with modulus sign. Thus we can make sure that this relation is also 0. So once this relation is 0, then again we can get, in this case, C1 is 0. Okay, this in both case, either that case or this case, we make sure that C1 is 0. Once C1 is 0, we replace N1 by N2, A1 by A2, etc. Then above procedure is applied to get C2. Then ultimately in m number of iterations, we can get all the coefficients are vanishing. So this way we are going to prove. Okay, so now we get into the situation. So just I am putting it a notation. So in this rest of the talk, A1, A2, AM are given integers, distinct integers, and enumerated this way. N1 is a large enough integer, and Ni's are going to be chosen like this, as N1 is a parameter. And hence because of Ni is defined like this, then we always get A1 N1 square minus A N square greater than or equal to 0. And then there are relations among Ni's depending on the situation. I am just restating it once again. Beta is a PV number of degree D, and Ca's are given algebraic integers in Q beta. Okay. So first, we prove that algebraic integer xn1, how to make sure that it is 0. It means the partial sum from the linear combination of series, we are coming down to same linear combination of partial sums with some suitable choice of Ni's. Okay, so okay, so already by multiplication multiplying by beta power A1 N1 square, xn1 is an algebraic integer. Now we have to compute only the norm. Okay, so we make sure that norm is strictly less than 1. Okay, so for that, this condition is required. This is again hypothetical only. In the real situation, we will be proving this relation of A times Ni plus R whole square minus A1 N1 square is greater than or equal to R times 2N1 plus R for every natural number R. Okay, now we estimate first. We estimate xn1. So when we estimate xn1, we can, xn1 is this, but the point is we have the series is given the lean. Therefore, x11 we can take it as in the tail side, because okay. So we estimate for beta we in the tail side. Okay. So this means okay. Okay, here the first sum somehow I missed that Ci's. Okay. Okay, in the inner sum, if you see that after multiplying by mod beta A1 N1 square, what you have in the denominator mod beta AI plus Ni plus R whole square minus A1 N1 square. This is the denominator it comes. So since we have the lower bound for each R, we have the lower bound, we can replace this by R into 2N1 plus R. So therefore, we can take out 2N1 plus R, we can take out because this is a tail. So it will start from the 2N plus 1, 2N1 plus 1. So we take out that, and H is the maximum of all the maximum of mod Ci, not only mod Ci, it is after applying sigma. Right now, you can take it to be maximum of mod Ci. Then we can make sure that the rest, once we take out this 1 by beta power 2n1 plus 1, we can make it rest all, it's a geometric series. Therefore, we can estimate it by beta minus 1. So this is less than or equal to 1 by beta power n1. N1 is our parameter. So here you will see that loose bound just because I have taken numerator to be 1. If I take the suitable functions in the numerator, then this can be better. Okay, well, we need it kind of 2n1 plus 1 we have to take out. Okay, this is for beta. We want to estimate the norm. Therefore, we have to estimate all the conjugates of x and 1. Okay, so we start with non-trivial embedding sigma from q beta to c, and we apply we consider sigma xn1. We just, it's a field homomorphism, so it just applied individually because we are looking at the finite sum in the from the definition. So for xn1 we looked at the tail, but here sigma xn1 we are looking at the definition itself. Okay, finite sum, because sigma is applied. Since beta is a PV number, that modulus of sigma beta is strictly less than 1. Okay, so therefore in the new whatever, if you see that in the numerator each summons, if I write it in the numerator, sigma beta whole power a1 n1 square minus a1 the ai little n square, where n is up to capital Ni. Okay, so this is always greater than or equal to 0 by first our assumption, and sigma beta is strictly less than 1 for every sigma non-trivial embedding. So therefore we can estimate it just trivially. So what comes out is maximum of sigma ci. So therefore h, I take it to be all sigma, maximum runs over all sigma and all I from 1 to m, 0 to m. Okay, so the h will come out, and whatever summoned is the max here. Ni, if you look at it, maximum is n1. Therefore, I just m plus 1 times n1. Okay, so therefore the norm of xn1 is if we estimate, what we get is it is a big O of 1 by beta power n1 power kappa. Kappa is less than or equal to 1, where the implied constant does not depend on the parameter n1. Okay, so therefore we can, for large enough n1s, we get the result, because we can make sure that this is less than 1, because constants are whatever constants are h times m plus 1. So this can be beaten by choosing n1 bigger. Okay, so this way, this is the main idea. Okay, for rest of the YAs in lemma 1, we, by the relation, this is the relation among NIs, we proved that xn1 is order of big O of beta power minus n1 power kappa for some positive kappa. However, this implication, this estimate for the other yn1 and zn1, for instance, yn1 comes in the second step, yn1 and zn1, this is straightforward, it will come. Okay, this is yn1. If we multiply after this, in 3, if you see that we don't need that estimate infinite series. So here only finite thing. Therefore, automatically the same kind of bound exists for zn1 also. So in lemma 1, okay, this implication is readily available from the definition of yn1 and zn1. To prove yn1, zn1 0, it is just enough to estimate their norms already. Okay, so the proof is just verbatim, nothing more, by just taking sigma to be non-trivial embedding, and instead of xn1 you apply yn1. So beta is a PV number, it takes care of it in some sense. Okay, now we get into the real case, in the sense of what we are trying to prove, that theorem. The case when square root of a1 by ai all are rationals. Okay, we separate this the proof by 3 cases. One is this case, square root of this quotient is rational number, and the second one is this numbers along with one is q linearly independent. Then the last case is that is a difficult case, is q linearly dependent. Okay, so when it is rational, how we choose infinitely many n's, that's what we are going to choose, n ones, the parameter we are going to choose. So d is the common denominator. Once these are all rational numbers, you choose d to be the common denominator. Then for any natural number n, nd square root of a1 by ai are all integers. So we choose t is a subset of infinite subset of n, which is all numbers looks like nd, n times d. So for this case, a1 n1 square minus a ni square is 0 by the definition. Okay, therefore we have to go through the two steps in order to prove the theorem. Okay, so in this setup, what we made, it is enough to compute only the relations. So rest all already it is there. So for lemma 1 is also abstractly proven. So therefore, it is enough to check in this case, the chosen ni's, for chosen ni's, whether this relation is true or not. That's all we have to check really. Okay, at least this is true for the first two case. This is the one we have to check. So this is what we are checking. So ai times ni plus r whole square minus a1 n1 square, the relation we want, how big it is, the lower bound. So this, because the a1 n1 square minus ai ni square is 0, whatever is left over is just the middle term and the last term. That's all. That is that you, since the square root of a1 ai, these are all a's are greater than or equal to 1. Therefore, you get the trivially this lower bound. Okay, so therefore, this once we have this relation, we can force xn1 to be 0. This is true for all n1 inside T in some sense. So in order to finish the proof, we have to check. This is since we don't have the lower bound, we have to go through the second case of the abstract proof. So therefore, we need to check two more relations among these ni's. Okay, so the first relation is a1 n1 minus 1 whole square minus ai ni minus 1 whole square. This is just when we compute, you see that the a1 is least and ai's are bigger than a1. Therefore, the first coefficient, I mean 2 times n1 times square root of a1 ai minus a1. This is a positive number. So therefore, this is like kappa times n1 for some positive kappa. Okay, so this okay. So now we choose r1 to be anything, some small kappa power of small kappa. Then this will, the second relation is first. The second relation also holds, just because the first two terms are 0, the subtracting a ni square minus a1 n1 square is 0. Therefore, r1 only. Just by choosing some values of kappa, you achieve these two together. Okay, so it means we prove C1 is 0 in this case. Okay. So then the rest is anyway by induction. So we are in the second case. Second case is Q linearly independent. Okay, this quotients, square root of this quotients are Q linearly independent. So in this case, each one is an irrational number. Each quotient a1 by ai is irrational for m minus 1 numbers. Then we want to get parameter, infinitely many parameter n1. So this is achieved by appealing to uniform distribution mod 1. Okay, so how we do this? This is an m minus 1 dimensional result we have to apply. So we take this particular, here am is the biggest integer, biggest among the given integer ai's. So we choose 1 by 10 power am plus 1 and by comma 1 by 10 power am. This very short interval inside 0, 1 whole power m minus 1. I have written just r power m minus 1. So in this, we are looking at the sequence alpha 2. Alpha 2 is nothing, alpha I nothing but square root of ai by a1 by ai. This is irrational, we know. So we are looking at the sequence alpha to n, alpha m n. This is the sequence inside r power m minus 1. This sequence, since 1 alpha 2 alpha m are q linearly independent, this sequence is uniformly distributed mod 1. That is this for the infinitely many values of n, capital N. This fractional part of capital N alpha I lie in this interval, the chosen interval. This is what our T is capturing, this n1s. This particular, we want to use this. We will work within this T. Okay, so we set Ni to be the integral part of square root of a1 by ai times n1 for all I equal to 2, 3 up to m. And using the fractional part lies in this short interval, we get hold of what is Ni lower bound and upper bound in terms of n1. We want to shift everything in terms of n1 so that we can able to check. Okay, so first we are looking at the first relation. Okay, so this is what we always like to check. That's why. So we are looking at the relation among ni's, the second relation in this setup, a1 n1 square minus ai ni square, how big it is. That's what this calculation is. Okay, that's what this calculation is. This is the first, after you just ai times ni square will be the ni, instead of ni square you put the upper bound for ni, that is upper bound for ni already in terms of n1 it is there. So the first the square part goes away and whatever remaining is the middle term and the last term, which is greater than or equal to kappa times n1. So therefore this will, okay. So the second one is we have to look at this relation in order to make sure that xn1 0. We want to compute this, whether this lower bound is like r times 2n1 plus r or not. Just same calculation only. So this will come straightforward. So therefore, with these two conditions, we can make sure that xn1 is 0 and then yn1 is also 0. Okay. So that means once you prove yn1 is 0, in this case, C1 will be automatic. Okay. So, okay. The difficult case, ultimately the difficult case is Q linearly dependent. Okay. So in this case, at least one of them we can assume to be irrational just because we have, if it is all are rational, we have proved the case. Therefore, we can assume one of the quotient, square root of this quotient is irrational. So we take out the maximal linearly independent set in this numbers given m minus 1 numbers. So we just by rewriting the indices, we assume that 1 square root of a1 by a2 etc. Square root of a1 by al is the maximal q linearly independent elements among this quotients. Therefore, what we have is some set of L numbers Q linearly independent, and the rest of them are written in terms of Q linear combination of this L numbers. Okay, so this is the situation we are in. So the main hurdle is how we are going to choose infinitely many natural numbers n, capital N, such that the fractional part is controlled in the same way in the previous case. Okay, so in this connection, what we prove, this is completely just a cooked up proof. For a given m greater than or equal to 3, we can always assume m greater than or equal to 3 just because m equal to 2 already it is proven that algebraically independent, therefore automatically Q linear independent will come. So therefore m is greater than or equal to 3 and L is at least 1. L is at least 1. So we have alpha 1, alpha 2, alpha L. These are all Q linearly independent and the rest of them are linear combination of these L numbers. Okay, that's the given situation. So where the b, j, k, these are all rational numbers. D is the fixed positive integer, which is divisible by the common denominator of b, j, k. These numbers. Okay. Then, so that linearly independent side is very clear. We are going to apply to uniform distribution mod 1. But with the same n, we want to do it for the other also. That's why this is kind of getting into trouble. Okay. So this is okay. So what all then what we prove, there exists a sufficiently small real number epsilon and small eta k, depending on this rational numbers, and m minus l integers, okay, positive integers, m minus l positive integers, capital L plus 1 up to capital M, Lm, the infinitely many positive integers capital N, such that the fractional part of n alpha k is controlled by epsilon square interval in this epsilon square interval, and the other fractional part is also kind of controlled. Okay, where this numbers and all very small, we will give the kind of sketch how we arrive at it. We call the left hand side the lower bound as al plus j of epsilon, and upper bound is bl plus j epsilon for some. Okay, so how we arrive at this, I will give a sketchy proof. For each j, of course, all alpha j's are positive. All alpha j's are positive means for each j in this interval 1, 2, 3 up to m minus l, this I'm looking at the condition 2. All alpha l plus j I'm looking at. This is positive. It means for each j, I can get hold of one coefficient which is positive, because alpha k's are also positive. Therefore, that's what I'm writing. So since alpha of L plus J is positive, there exists a natural number Kj, J dependent, such that Bjkj is positive. Therefore, we choose positive integers E1, E2, El such that this relation is always positive after that. You multiply huge number, okay, huge number here kj is bjkj is the positive coefficient. We multiply a huge integer, positive integer, with this particular coefficient, and then we can make sure that this linear combination is positive. Okay, so for all j equal to 1, 2, 3 up to m minus l, then we choose epsilon to be from this given. H is a given positive integer, it's in our hand, and D is the denominator of all these rational numbers, and we are multiplying by this, and then we take huge and take the inverse of it. Okay, so epsilon is really tiny. So what is Ek? Eta k is epsilon times whatever Ek is, epsilon times eta k, Ek is. Okay, so k is from 1 to L. So the eta k's are coming, eta k's are determining the interval inside 0, 1. Okay, so this Lj plus, that is a integer, is defined to be, so once we multiply by the denominator, common denominator D times bjk is an integer, and we multiply by ek is coming from that way. Then therefore this is an integer, it is a positive integer. Capital L plus 1, etc. Capital M, these are all positive integers. Okay, with this setup, we first apply uniform distribution mod 1 for 1 alpha 1 alpha to alpha L Q-linear independent set. We appeal to the sub interval, okay, eta k eta k plus epsilon cube. Okay, that is E is the subset of R power L. So from this, we can get infinitely many in capital N's natural numbers such that n, the fractional part of n alpha k lies in this interval for each n. Now, however, we need to estimate the fractional parts of the rest of the alpha j's when we multiply by this n coming from this t. Okay, n times alpha L plus J is just I'm multiplying by n from the definition of alpha L plus J. Then n alpha k, I'm just writing it as an integral part and fractional part. And then I'm multiplying by d, the common denominator. Okay, so why we do this? Because of this. Okay, so we can estimate, okay, after multiplying by d, the fractional part side can be estimated using n alpha k. N alpha k, the k is coming from 1 to L. Therefore, we know the lower and upper bound. Using that, we can estimate this sum. Okay, so, and we want to prove that this particular thing is nothing but the fractional part of nd alpha L plus J. Okay, that one can, by the choice of epsilon, etc., we can able to make sure this is equal to this. But what we want to really estimate is n times alpha L plus J. This is what we want to estimate, the fractional part. But what we could estimate is n d times. Okay, so we just do this. We start with the fractional part of n d alpha. Instead of in the indices, just I'm putting alpha. N d alpha, just write it as that number minus the integral part. Then d times n alpha. D times n alpha, I'm writing it as integral part and fractional part. Then by adjusting, what we got is kind of the fractional part of n alpha. We want this is in between kind of thing. Okay, so now we appeal to Hermite identity. Hermite identity says this integral part of n alpha is less than or equal to n times integral part of alpha plus n minus 1, and at least it is n times alpha. Okay, therefore, since these n's are coming from T, the infinite subset, this therefore there exists another subset T naught, okay, this is infinite subset T naught of T, for which okay, this particular thing will be R, some R value. This D times fractional part of n alpha minus d times integral part of n alpha minus integral part of n d alpha. This is equal to R, fixed R, for infinitely many values of n. Okay, inside T naught. That R is coming from, because of this Hermite identity, R is nothing but it can be 0 or it floating from R to d minus 1. Okay, so we can get hold of one infinite subset where the parameters, our parameter n1 is running, and we can able to get this kind of estimates. Okay, for all uniformly. Okay, so now I'm going to just how we proceeded. Okay, the proof of the linearly dependent case, we choose ni to be the same way as we have done before. And first condition, we want to prove xn1 to be 0. Right now here n1 parameter is coming from T naught. That's the only thing. The first, in order to prove that, we just check this relation. I didn't do the computation because right now we have to check two cases for I equal to 2 to L and j equal to 1 to m minus L. These two cases we have to separately do using the already inequality we got. And then so okay, so with this condition we can force xn1 to be 0. The other condition, a1 n1 square minus ai ni square is greater than or equal to some kappa times n1. That we can able to get in this case. No, in this case we cannot. Okay, again two sub cases coming. what are the subcases when R is 0 and R is non-zero. So the R is 0 means it is coming from the Hermite identity. R is 0 means we are in the better case. The fractional part of n alpha is same as fractional part nd alpha divided by d. Okay, so that better case. So then the other case kind of break into two subcases, but we are in always in the this particular case only, in the sense. Okay, I'll come to the notation. Okay, we are always in the better a1 n1 square minus a ni square is bigger than or equal to n1 greater than or equal to n1 kappa. That is the case. So in the second two steps we can able to get, but here the computation is more, unfortunately. So I did not do the computation. I just finished.
Thank you, Sankara. Anybody has any questions or comments? Unmute yourself and ask. Okay, so if there are no more questions, so let's thank the speaker again, and let's thank all the speakers of the morning session or afternoon, whatever the timing is. Professor Sparlinsky, Professor Kaninika, and Professor Thangadare. And we have a small 20 minutes break now, and the next talk will start at 4:30, and Professor Ramare will chair the next session. So see you everybody in 20 minutes. Thank you once again.
Stop sharing. I will leave.
Adhikari. Sukumar. Adhikari. Adhikari, how are you?
അതാ ഓ ഫ്രണ്ട് പേസാണ്ടി മച്ചനർ
Yes, sir, what? Hi.
Hello.
Hi, Olivier.
Yes.
I think James is here also.
Yep, I'm here.
Good. And where are you?
Yeah, I'm here.
No, but where are you, James?
Oh, okay.
You're in UK?
Yeah, I'm in Oxford.
Okay.
So Olivier is going to chair the session.
Yes,
So
I am the chief.
Yes. So I will leave it to Olivier to decide what. I have made both of you co-host if James wants to share his slides.
So you're the new Shaoli?
Sorry?
You're the new Shaoli?
Yeah.
Because this morning you didn't look the same.
Yes.
Hi, Laurie.
Hello.
Hi.
Hi.
Okay, I'll start sharing my screen now.
Yes. Well, we'll start at say 2 minutes past 12, something like that. Time for people to join.
Well, yeah, you're the boss, so just tell me when you want me to start.
Yes. So you have some curfew? You have some...
Yeah, at the moment, like all shops are closed, and basically at the moment, there's a fairly strict lockdown in the UK.
Okay. While in Marseille, it's about okay, but no restaurant, no bars. We can still go out. We just have to be home at 6 o'clock in the evening.
Ah, okay. So there's a curfew. Yeah.
Yes, yeah. So when the conference stops, I have to stay home. You're using an automatic background?
Okay, so Oxford does lots of things on Teams where it blurs the background automatically, and I quite like that because often my office is really messy.
Okay.
But I couldn't find a way of doing it easily on Zoom. So actually, this is a picture of my office that I took with my webcam that I blurred, and then I used that as a background. So I went to surprising lengths to recreate the thing on Teams. On Zoom, just to disguise how messy I am.
Well, I mean, my office is rather messy, but the webcam goes on top, so you don't you don't see the desk.
Yeah, that's the other way of doing it.
Yeah. Just I saw the James. I
Yep.
saw the topic of your lecture. Did you talk with Henrik Ivanet on this subject?
I haven't talked to him, no.
Because maybe 7 or 10 years back, he was telling me that that he was able to prove Riemann hypothesis if he assumed that the zeros were on a finite number of vertical lines.
Oh, I didn't know that.
Anyway, it's if you
okay, yeah, I should talk to him about that.
Yeah, if you meet him, just. But I don't I have no idea of the proof. I just remember him telling me that, but no idea whatsoever what it was like. So the number of participants is increasing, 55. Well, okay, well, we'll start quietly. So, hello everyone. It's very funny to chair a session without seeing anyone. A bit like giving a lecture without seeing people. Anyway, we start this afternoon session with James Maynard from Oxford, and he's actually in Oxford. And he will talk to us about half-isolated zeros and zero density estimates. I think we can start now, please.
Okay, great. So thanks a lot for the introduction, Olivier, and thanks a lot to the organizers for inviting me to speak here. I'm very happy to be talking about this at Balu Fest. And maybe before I start, I should just mention that everything I'm going to talk about today is joint work with Carl Pratt, who's also here in Oxford. And I guess a slight health warning is that we're still in the process of just writing up all the details. So this is very slightly work in progress. And so correspondingly, yeah, there's a slight health warning with everything that I'm saying, although we're pretty confident that everything's correct. So I'd like to talk about half-isolated zeros and zero density estimates, but to set the scene, we can start off with the Riemann hypothesis that I'm sure everyone knows and loves, that all the zeros of the zeta function have real part equal to 1/2. And the reason we care about the Riemann hypothesis is that it has lots of nice consequences for the distribution of prime numbers. So two of my favorite consequences are the fact that you get almost Legendre's conjecture that there's a prime between any two consecutive squares, that if you're looking at primes in intervals of length slightly larger than the square root of x, then you get an asymptotic formula for the number of these primes automatically if you assume the Riemann hypothesis. And then there's also a result of Silberg where you get an asymptotic for primes in almost all short intervals, provided your intervals are maybe a bit bigger than log of x all squared. So the Riemann hypothesis is just a statement about zeros of the zeta function, but at least the reason I care about it is that you have lots of nice consequences for the distribution of primes, and in particular the distribution of primes in short intervals. But unfortunately, the Riemann hypothesis seems hard to prove. But one nice thing is that if all you care about is the consequences for primes in short intervals, then actually you don't need something quite as strong as the Riemann hypothesis itself. So for lots of these arithmetic applications towards primes, certainly not all of them, it's often sufficient to show that most zeros lie close to the half line rather than all zeros. So one way of measuring this is to let n sigma t be the count of the number of zeros with real part at least sigma and imaginary part at most t. So we're just counting zeros in a box. We know all the zeros have real part less than or equal to 1. So we're given some number sigma and some number t, and n sigma t just counts the number of zeros in this box here. And it turns out that if you have good bounds on n of sigma t, then you're showing that there are few zeros of moderate height that lie close to, that lie far away from the half line. And this is actually sufficient for proven results about primes in short intervals. So this is all very well known, but if, as a black box, you gave me a bound of the form n of sigma t is bounded above by t to some constant a times 1 minus sigma, then for the asymptotic for primes in short intervals, I get this whenever y is bigger than x to the power 1 minus 1 over a. And the proof of this is very short, and it's maybe quite illustrative for some of the things I would like to say later on in this talk. So I thought I would give a 3-line sketch. You want to understand primes in short intervals, so it's sufficient to understand the von Mangold function in short intervals. And you can use the explicit formula to write this as a main term, which is what we'd expect, and then plus some fluctuation, which is determined by the zeros of the zeta function. And I may be suppressing some small error terms and things here, so I'm lying slightly, but essentially the number of primes, the count of primes in the short interval has our main term, and then some what we expect to be an error term coming from zeros of height at most x over y. And I can split this count up according to the size of the real part, and I can bound the number of zeros with real part approximately equal to sigma by n of sigma t. And so I can just trivially bound this sum over zeros in terms of n of sigma t. And if I just plug in the bound that I'm assuming, then I see that whenever y is bigger than x to the 1 minus 1 over a, then n of sigma x over y is a bit smaller than x to the power 1 minus sigma. And so this gives us an asymptotic formula for the number of primes in short intervals. And the best known zero density result is a result due to Huxley, at least of the best known zero density result when it's just of the form t to some constant times 1 minus sigma, which is maybe the most important form of zero density results. It's this result of Huxley that n of sigma t is bounded above by t to the power 2.4 times 1 minus sigma. And so an immediate consequence of Huxley's zero density bound using the previous lemma is that we get an asymptotic for primes in short intervals where the length of the interval is about x to the 7/12 or slightly bigger. And Huxley's result is almost 50 years old, but essentially there's been no improvement on this zero density bound. And for the question of short intervals where we get an asymptotic formula for the number of primes, Heath Brown has essentially been able to replace a plus epsilon. He's been able to remove the plus epsilon, but otherwise this is essentially still the best known result for primes in short intervals and hasn't seen any improvement for 50 years. Similarly, you automatically get good results about primes in almost all short intervals, and those are also essentially the best known results. However, we believe that you should be able to improve this bound on n of sigma t, and the density hypothesis is the claim that you should be able to improve Huxley's 2.4 to the constant 2. And this is somehow a very natural limitation of lots of the methods used to study questions to do with the density hypothesis. Of course, we expect that n of sigma t should be equal to 0 as soon as sigma is bigger than 1/2. But the density hypothesis maybe represents one of the most optimistic extensions of the sorts of results that we typically use to study primes in these problems. And the nice thing about the density hypothesis is that from the point of view of primes in short intervals, or primes in almost all short intervals, this is almost as good as the Riemann hypothesis itself. So for example, you get an asymptotic formula for the number of primes in short intervals whenever y is slightly bigger than the square root of x, just in the same sort of range as we got with the Riemann hypothesis. And again, just falling short of Legendre's conjecture. So for at least the point of view of primes in short intervals, the density hypothesis seems like a possible substitute for the Riemann hypothesis, but we might hope that the density hypothesis is quite a lot easier to prove. And we can prove results in this direction, which give us the best partial results. So this is Huxley's result, but unfortunately, the density hypothesis still seems difficult right now. But let's imagine we wanted to try and improve upon Huxley's result on primes in short intervals. So if you go through the sketch proof of the lemma that I wrote, you'll see that the key thing is to understand and get a good bound for this sum over zeros. And it turns out that if you go through Huxley's work, combining it with the earlier work of Ingham, you actually get you can improve the constant 2.4 to something slightly smaller unless sigma's very close to 3/4. So this means that if you want to get an improvement on results about primes in short intervals, you really only have to worry about zeros of the zeta function, which have real part very close to 3/4. And if you can get some bound on this sum over zeros, which occurs, that's non-trivial, so some improved bound, then you would expect to get an improvement in the length of the short interval that you can handle and still get an asymptotic formula for. So a couple of comments about this sort of sum. Even if there were lots of zeros, you might expect that this sum should actually have quite a lot of cancellation within it. And so if there was lots of cancellation, you would quite easily get results about primes in short intervals without necessarily needing to improve on zero density results. However, you would need to understand something about the distribution of these putative zeros if you were to show that there was cancellation, because if it was the case that there was some value x0 and x to the I gamma, where gamma goes through the imaginary parts of the zeros on the 3/4 line, if x0 to the I gamma all pointed in the same direction, say they were very close to being real numbers, then you would have essentially no cancellation in this sum, and your only way of trying to prove anything would be to prove that there are a few different zeros on this 3/4 line, or close to the 3/4 line. So in particular, there's a very clear obstruction to making any progress, which would be the problem of there being lots of zeros on the 3/4 line in a particular arithmetic progression. So sets of zeros in arithmetic progressions on the 3/4 line would be a very strong way of obstructing progress on primes in short intervals and lots of other related results about primes. And this sort of obstruction actually appears in quite a few different places. For example, if you started having arithmetic progressions of low-lying zeros for certain Dirichlet-Yale functions, this would also cause various unexpected behavior and problems in questions about, say, Chebyshev's bias and things like that. but it's a common obstruction that you run into, that there could be these arithmetic progressions of zeros as you go up the imaginary line. So the main result that I'd like to talk about today is a new zero detecting mechanism for what we call half isolated zeros. And the key thing that I like about this is that it's rather different to the standard zero detected mechanisms, and in particular, it's somewhat sensitive to the precise vertical distribution of zeros of the zeta function. So most zero detecting mechanisms essentially are sensitive to the horizontal distribution, but they say nothing at all about the vertical distribution. And so in particular, this is somewhat addressing the potential problem that I mentioned on the last slide about arithmetic progressions of zeros on certain vertical lines. And this work was at least partially inspired by some much earlier work. So there was an unpublished note of Heath Brown on isolated zeros of the zeta function. And this was also picked up on and extended in a paper of Balasubramanian and Ramachandra. So it's very nice to be able to speak about something that was inspired by Balasubramanian's work in this conference. So before I get into precisely what this new zero detector mechanism is and what I mean by half isolated zeros, which is maybe slightly technical, even though I view that as the kind of main idea, I'd like to state a couple of consequences of this new unconditional zero detecting mechanism, which works very well if there's a certain amount of rigidity in the distribution of the zeros of the zeta function. So for example, imagine that the zeros of the zeta function lie on finitely many different vertical lines. Under this assumption, our zero detecting mechanism works very well, and we get improved zero density estimates. So we can improve this 50-year-old bound of Huxley, and also a now maybe almost 80-year-old bound of Ingham to get a improved zero density estimate. And correspondingly, if you improve zero density estimates, you improve results about primes in short intervals. So you get a improved result on the length of intervals where you can count the number of primes. So I should mention that we should be able to do a little bit better than 13/24 for counting primes in short intervals, although that's part of the write-ups are still in progress, and we can certainly get 13/24, so maybe we'll leave it like that. And we're stating the assumption that the zeros lie on finitely many vertical lines, because I feel it's the cleanest way of presenting our results, but we can certainly have much weaker but more technical assumptions. And the main point of this is slightly less conditional results, but we hope that this might lead to a new unconditional approach about primes in short intervals, although there's certainly new ideas are required if you're going to, say, make this corollary unconditional. So maybe that's a good flavor of the sorts of results that we're getting and the sorts of consequences we get from this zero detecting mechanism. But maybe I'll try and say a little bit more about what it is that we're really doing and what I mean by these so-called half isolated zeros. So I'm going to call a zero of the zeta function half isolated if every nearby zero either lies to the left of this zero or it lies above the zero. So it's roughly saying that there's no zeros to the right but that's maybe not such a strong assumption because you expect, and we also partially know, that as you go further to the right, the zeros become rarer. And we're also saying that somehow there's no zeros directly below this half isolated zero. So it's half isolated because it's isolated to the right and it's isolated below, but it's not necessarily isolated above. And it's these zeros that we develop a new way of counting, and we can count these zeros unconditionally. So the work of Heath Brown and Balasubramanian Ramachandra, so RB should be BR, they showed a somewhat similar result under the rather simpler assumption that all the zeros were just to the left. And if all the zeros were to the left, then somehow zeros to the left become trivial in this setup. And so the number of such isolated zeros satisfies a density hypothesis type bound. So given that context, the key improvement that we have is that we're extending isolated to half isolated, which becomes a lot more technical to deal with. And so then maybe our main theorem is that there exists a short Dirichlet polynomial which takes large values near half isolated zeros. So maybe I'm lying very slightly in this statement, but there exists a Dirichlet polynomial with coefficients of size 1, which is a very short Dirichlet polynomial. So if you're looking at half isolated zeros of height t, then this Dirichlet polynomial only has length t to the epsilon, and this Dirichlet polynomial takes a large value, so it's close to 1 in size whenever it's evaluated at a half isolated zero. So you'd expect as soon as you're away from the, well, I guess you'd expect that normally a Dirichlet polynomial should be taking exceptionally small values. So these large values are very rare, and therefore this is really detecting an unusual event. And the reason that this half isolated zero detector then gives various nice consequences if you assume that the zeros lie on finitely many vertical lines is because we start to get some fairly good distributional information about the vertical distribution of zeros of the zeta function. So if the zeros do lie on finitely many vertical lines, then they have to form these clusters above a single half isolated zero. So you can either a zero is half isolated, or there is a nearby zero on the same vertical line which lies below it, and you can just keep on therefore passing down, and so the zeros come in these clumps all lining up above a single half isolated zero. So in this diagram, you're supposed to be thinking about there being 3 vertical lines, sigma 1, sigma 2, and sigma 3, and the red crosses are supposed to denote half isolated zeros where there's no nearby zero below them, and the black crosses are not half isolated zeros, but they must all be occurring in some cluster above a half isolated zero.
James, does this say anything about what happens on the critical line?
No, not really. This is really only talking about things that happen away from the critical line. That on the critical line, suddenly it's not abnormal for such a Dirichlet polynomial to be taking large values, and so it doesn't really have any content. But as soon as you move away from the critical line, this is having non-trivial content.
Okay, thanks.
And so if you, since you have this nice clustering behavior, you suddenly have this fairly strong information about the vertical distribution of zeros away from the half line. And you can then work this into lots of traditional techniques for detecting zeros. In particular, it's combining this with the previous zero density type technology and making use of this clustering behavior that allows us to prove conditionally new zero density results if the zeros lie on finitely many vertical lines. And in particular, if the clusters are always small, as you might naively expect if zeros are somewhat rare, then you suddenly get very strong bounds. So if you imagine that all the zeros occur in clusters of length big O to the epsilon, then this short zero detector would give not only the density hypothesis that n of sigma t is bounded above by t to the power 2 minus 2 sigma, and so in particular would give an asymptotic for primes and short intervals of length slightly bigger than the square root of x. We'd also get a essentially sharp bound for the fifth moment of the zeta function. So at the moment, we know how to bound the first four moments, but we don't even know how to bound the 4 plus delta moment for any small delta, whereas we get the fifth moment if you assume that zeros lie on finitely many vertical lines, and then these clusters are all small. So quite a strong assumption, but strong and nice consequences if you make this strong assumption. So maybe before I move on, I'll just pause here to check that everyone is reasonably happy with what I'm claiming this main result is and how this corresponds. So the main result is unconditional about these half isolated zeros, but then if you combine it with the assumption of the zeros line on finitely many vertical lines, then this automatically gives some nice arithmetic consequences. Okay, seeing no questions or objections, I'll assume that everyone is happy with the main statement, and I'll move on to talk about some of the ideas that go into this argument. So maybe before I go into, maybe I'll start out with just a basic attack, which also incorporates the work of Heath Brown and Balasubramanian and Ramachandra. So you can just take your favorite smooth, non-negative function reported on the interval 1 up to 2, and let this have Mellin transform capital W. So little w is the smooth function, capital W is the Mellin transform. And I'm now going to consider the following sum. So it's just going to be lambda of n, little w of little n divided by capital N divided by n to the rho naught. So you should think of this, so this sum is supported on values of little n between capital N and 2 capital N. And so we should think of this as maybe some Dirichlet polynomial of length capital N evaluated at a half isolated zero rho naught. But for the moment, I'm not even going to assume that we can just think of rho naught as maybe some zero of the zeta function. So by Mellin inversion, I can just rewrite little w in terms of its Mellin transform capital W, and then I pull out the well-known Dirichlet series for the von Rangeldt function, and this n to the rho naught on the denominator just means that I'm shifting the argument slightly. I have this contour integral, and the obvious thing to do is to move the integral to the left. I pick up poles according to when the argument of zeta primed over zeta is equal to 1, or when the argument of zeta primed over zeta is equal to rho for some zero of the zeta function. And I get some leftover contour that's basically negligible, so I'm going to ignore it. So essentially, I can approximate this contour integral as the sum over all the residues. But since I've assumed that my function little w is smooth and nice, this means the Mellin transform capital W has very rapid decay. And so it turns out that essentially all the terms coming from these residues are completely negligible unless the argument of capital W is very small. And this means that up to some tiny error, this whole quantity basically reduces down to a sum over zeros, which are very close to our original point rho zero. So if rho zero itself is a genuine zero of the zeta function, then that appears in this sum, because certainly rho zero minus rho zero is less than log t squared, and that contributes a quantity which is of size about 1. So if there were no other zeros at all which appeared in this sum, then this would mean that we would have shown that this Dirichlet polynomial, which is quite short on the left-hand side, takes a large value at rho zero, because rho zero would basically be the only term, and the whole thing would be of size 1. Similarly, if maybe rho zero isn't the only zero, but all the other nearby zeros that occur in this sum have small real parts, then n to the rho minus rho zero will be n to some negative power, and so all the contribution from each of these other zeros is also going to be small. So if all the zeros have real part less than the real part of rho naught minus epsilon, so they all lie to the left of rho zero, then essentially they contribute a negligible amount. And so again, the contribution from rho zero dominates. And this is basically the argument of Heath Brown and Balasubramanian and Ramachandra, that if we have an isolated zero rho naught, then the contribution from rho naught dominates the right-hand side, and this means that there's a large value of this short Dirichlet polynomial. And this is how they're able to show that isolated zeros have short zero detectors. Unfortunately, this whole argument completely breaks down if you have maybe many zeros close to rho zero, which don't necessarily lie to the left of rho zero. So we would like to, a natural thing to try and do is to try and understand this argument and try and refine it to say also include these, to also include zeros that aren't isolated, and certainly to include half isolated zeros. So a natural question then is it always the case that when you have a zero, when you're evaluating at a zero rho naught, the right-hand side is large? It might be the case that even if you had lots of zeros nearby, the contribution from rho zero always dominates in the way that it dominates when you have an isolated zero. So it's not too difficult to see that basically regardless of what configuration of zeros you had, if there's zeros with if there's several zeros with similar real parts, then there are values of n and there are choices of capital N and your smooth function w, which means that certainly the sum can sometimes be very small. So maybe the next question would be, well, okay, there may be some bad choices of little w and capital N, but is it possible for this sum over zeros to really be uniformly small for all choices of capital N under consideration and all possible choices of smooth functions? It feels like we have a huge amount of flexibility to choose these, and provided we can find a good N and a good choice of little w for every 0 row naught, then we should be able to construct something that at least looks like a short zero detector from that. But unfortunately, it can be the case that this sum is uniformly small if the devil is allowed to place where the zeros close to row 0 are. And again, it turns out that it's our familiar enemy of the zeros lying locally in a vertical arithmetic progression. So if the zeros nearby to row 0 lie on a vertical arithmetic progression with common difference some constant divided by log t when we're working at height t, then for every choice of small n and every choice of smooth function w, this sum is actually tiny. And this means that if you were just in the middle of a vertical arithmetic progression of this type, somehow this approach of trying to find a short zero detector feels like it's doomed to fail. And we don't see any way around this at all. This common obstruction of arithmetic progressions on vertical lines seems to completely kill this approach. However, this very much relies on the fact that you're in the middle of a very smooth local distribution. And if there's somehow a discontinuity in the local distribution of zeros, such as the case with half isolated zeros, where zeros lie above, but they don't lie below, even if they lie in an arithmetic progression above, this whole argument, this whole obstruction goes away. And whenever there's some sort of disruption to a very regular local distribution, then I at least am not aware of any obstruction of this type. So it's only things that look like arithmetic progressions or unions of arithmetic progressions that I'm aware of that really causes obstruction, that for every choice of capital N and every choice of smooth function, this sum over nearby zeros is very small. So you might therefore hope that you could prove something to say, if the zeros don't look like they lie close to some union of arithmetic progressions, or when, at least when you're looking close to row 0, then there is some good choice of capital N and some good choice of smooth function, which would allow you to create a short zero detecting polynomial. And we are able to do this, at least in the special case of half isolated zeros, where nearby zeros don't differ too much in their real parts, and they all lie vertically above the zero that we're interested in, row 0. And the key to this, which is maybe of independent interest, is a refined sort of Chuan power sum type estimate. So maybe the simplest formulation is, if you pick your favorite R real numbers, then if you give me any superdyadic interval, then I can find some argument capital N for which this sum, which is modeling the sum that we had before, is not too small. So it's lower bounded by some polynomial quantity in the number of reals that we have. So you could apply standard estimates coming from Chern power sums, and that would show that there's some value of n in such an interval where the lower bound is instead exponentially small. So we get this sort of exponential improvement from an exponential lower bound to just a polynomial lower bound. And the fact that we can get this polynomial lower bound is absolutely vital for our method. So maybe a few remarks. Traditionally in Chern power sums, you look at integer powers of some fixed complex numbers. So you may be thinking about evaluating this sum S at powers of E, so maybe e to the L for integers L. But then the lemma would be false if you restricted to just a discrete set like this. So it's actually very important for our method that we allow completely arbitrary real numbers n within the superdyadic interval, and we're not restricting to some sort of well-separated set of reals. Because you can have counterexamples to the main statement then. Similarly, it's absolutely vital for our method that you have some positivity in the coefficients. So actually it's important for us to have a rather weaker statement than just all the coefficients are +1. And we do allow for some negativity, but if you are allowing for arbitrary ±1 coefficients, then you could choose theta j such that this sum Sn was just the expansion of 1 minus n to the power I divided by 2 log m to the power k. And the point here is that whenever n is between m and m squared, this quantity is going to be exponentially small. And this will show that you couldn't possibly have a polynomial lower bound. So it's very important, therefore, that we don't allow arbitrary ±1 coefficients. And so we have some sort of positivity in our setup. I guess, as we mentioned beforehand, it's also very important that we have some sort of discontinuity in our coefficients, because we saw that if you're allowing smooth coefficients that can decay, then this sum can be uniformly small. And again, it can be almost exponentially small. So it's very important that there's this discontinuity, that we're summing discrete points, and the weights are either, at least in this context, 0 or 1, rather than having smooth weights. And the final point is that there are some choices of theta j when S of n can be polynomially small for all choices of capital N. And so up to the constant 100 here that we haven't tried to optimize, this is essentially best possible in this setup. So this is a very simplified setup. It's very much in the Chern power sum type setting, but it turns out that this sort of estimate is the key to allowing us to detect half-isolated zeros. So maybe I'll go through relatively quickly, but just the idea behind this power sum lemma is that since S of n is essentially an analytic function in n, we can understand Sn in terms of complex values of n. So just the basic principle that if you want to understand an analytic function, you can understand it on a wider complex domain and give lots of information about values within the complex domain. So we consider this related complex analytic function f of z, where I'm basically writing n as e to the power z. And clearly, at least in this setup, I can assume that θ1 is the smallest of the real numbers and that θ1 is equal to 0, because that doesn't change the modulus of the sum at all. And then if I evaluate this at purely imaginary arguments, because all the coefficients are 1, all of these terms become real then, and just the first term from θ1 gives me a constant 1. And so I know that at any purely imaginary argument, this sum always takes fairly large values. In particular, it's always lower bounded by 1. But on the other hand, I know that since f is analytic, the logarithm of the absolute value is subharmonic. So just to remind everyone, that means its value at a given complex number is upper bounded by the average of its value on a circle around that complex number. And so applying this to this complex number f of I log m, we see that we can apply this with bigger and bigger and bigger regions. So I can think about applying subharmonicity to ever-growing boxes, which are increasing to the upper half plane. And provided the function has sub-exponential growth, I can then bound the value at some complex point by a integral along the real line. So I can upper bound this large value by its values along the real line. And then just by using the trivial bounds that we've already seen, it follows straight away from this subharmonic inequality that f can't be very small on a whole dyadic interval, which corresponds to the original result. So it should be mentioned that when we came up with the proof of this, we were quite pleased with this, but we were trying to find if something had been done in the literature beforehand, because it sort of felt vaguely reminiscent of some of the arguments that occur with Hardy spaces and things like this. We weren't really able to find anything apart from, we contacted Jean Bourgain about it, and Jean Bourgain gave a independent proof of the same result, basically using the same ideas. And we also found that there was a Math Overflow post by Will Sarwin, who also comes up with essentially the same, fundamentally the same argument. But anyway, how does this relate to half isolated zeros? So if you recall, we'd like to show that this local sum of zeros near a given zero, row 0, is large to show that there's a short zero detecting polynomial. So zeros to the left trivially contribute some tiny amount in the same way that they trivially contributed a negligible amount when in the Heath Brown or Balasubramanian Ramachandra results. If the zeros, say, perfectly lined up on a vertical line, then this starts to look exactly like the situation that we had before, where theta j is just given by the difference in the imaginary parts, gamma j minus gamma 0. And okay, we have this slight extra complication from the smooth weight w, but we can say choose w so that it's non-negative on the imaginary axis, and we still have this discontinuity because we know that all the zeros lie above row 0 whenever row 0 is half isolated. And then you can adapt that Duran power sum type lemma to also handle this slightly more general situation, and that shows that there must be some value of n between, say, t to the epsilon and t to the 2 epsilon, which gives a large value, and so therefore proves the existence of a short zero detector for half isolated zeros. And so the key point is that it being half isolated and all the nearby zeros kind of crucially lying above the zero causes this discontinuity that's necessary in our Turan power sum type lemma. So as soon as you have short zero detectors, there's lots of techniques that you can start to use. So the mean value theorem for Dirichlet polynomials becomes very powerful and automatically proves a density hypothesis type bound for half isolated zeros. So an immediate consequence of this is the number of these half isolated zeros in a box with imaginary part at most t and real part at least sigma is of size at most t to the 2 minus 2 sigma. And moreover, if you assume that the zeros lie on finitely many vertical lines, then we can really start to use this vertical structure that we now know that zeros must have, that there must be some small number of half isolated zeros, and then these dense clusters of zeros lying directly above the half isolated zeros. You trivially get a bound that if you're looking at clusters of length h, the number of total zeros is, well, the number of half isolated zeros times the number of zeros in a cluster. So it's bounded by h times t to the 2 minus 2 sigma. So you can refine this slightly, but this shows that you get a good bound for the number of zeros on the line with real part equal to sigma whenever you are looking at h being small, and so small clusters. And so the question then is, can I also get a good bound if I have much longer clusters when h is quite big? And so I would have these like very long, dense clusters of zeros, maybe on the 3/4 line. And this lemma is maybe a proof of concept that you can do better. And this is just exploiting the new clustering information with more standard zero detecting techniques. So again, in the interest of time, maybe I'll be slightly short, but the standard zero detecting techniques say that there is some Dirichlet polynomial of length m, which takes large values at any given zero. So this is different to what we had before, because these Dirichlet polynomials are not necessarily short Dirichlet polynomials. They could now be quite long Dirichlet polynomials. But if we're thinking of m taking a value of size m to the sigma whenever it's evaluated at a point with imaginary argument very close to zero, then we can exploit clustering by saying, if I look at this integral of m to the power 4 evaluated at it times m to the power 2 evaluated at it plus ih, and integrate between t and 2t, and little h going between minus h and capital H, then whenever we're close to a zero, whenever it is close to the imaginary part of a zero, m of it is taking the value m to the sigma. But we also know that whenever we have a zero at it, if it's part of a cluster of length capital H, then all of these shifts, m of it plus ih, are also taking large values. And so the number of zeros that occur in clusters of length h provides a lower bound for this sum, and we see that it's of size r times h times n to the 6 sigma, since there's 6 copies of m, which all take in values of size m to the sigma, and where there's h different zeros in each cluster that are picked up by this h integration. But on the other hand, we can sort of fairly straightforwardly estimate this sum, and it turns out that you can bound it just by some Diophantine counting problem, and so you can get a fairly sharp bound for this using variance of the mean value theorem. And this simple bound here then gives an upper bound for R, which becomes very strong and much stronger than more traditional zero detecting mechanisms whenever capital H is large. So we're exploiting this clustering effect to get improved zero density estimates in this case. So if you combine this simple clustering bound with more complicated variants, but in the same sort of spirit, this gives our new improved zero density estimate when the zeros lie on finitely many vertical lines. And one interesting thing is the worst case scenario now is no longer when sigma is close to 3/4, it's when sigma is close to 2/3. Okay, I'm basically out of time, but as I mentioned at the beginning, our hope is that this is a new way of attacking questions about primes and short intervals that might lead to new unconditional zero density estimates. But there's one enemy scenario that we really don't know how to rule out. And so if you want to make progress on primes and short intervals using this line of attack, we need to rule out what we call bows of zeros, which cause problems. And we can think of this as the imaginary parts of zeros increase as if they're in an arithmetic progression, but the real parts smoothly increase from 1/2 up to whatever bad value of sigma that we're thinking of, and then smoothly decay back down to 1/2. And this is difficult for both of the two techniques that we're using, because if you look very locally, then the real parts hardly change at all. And so the zeros always look as if they're in the middle of an arithmetic progression. And so there's no discontinuity there. But then globally, because the real point, because these zeros are somehow connected to zeros on the half line, we can't use the clustering techniques that we're able to exploit in other situations. And this means that we don't have more global ways of exploiting these situations. And so somehow it doesn't work on either the local side or the global side. And so both of the two techniques that we're using to get these improvements fail to work in this situation. But morally, I feel that if you can handle this, then you're maybe well on the way to getting improved results about primes and short intervals and zero density estimates. So maybe I'll stop there. Thanks a lot for everyone for listening, and congratulations to Bala Subramanian and happy birthday.
So thank you, James. I don't know whether people can unmute to clap. So clapping is difficult at distance. If anyone has questions, well, I have lots of questions for this beautiful talk. A very simple one about this power sum like estimate. You have a lower bound which is 1/r to the 100. Well, and you have an example of 1/r. Do you have any idea of what should be the answer?
No is the short answer. That yeah, so I think the example does a little bit better than 1/r, but somehow the example doesn't feel terribly natural. So I would expect that the example is not the worst case scenario. Similarly, our method will give something a bit better than 100, although we haven't really optimized it. There's clearly still quite a large gap between the constants. The constants don't matter at all for our applications, but I would expect that neither the upper bound nor the lower bound are correct, and I really don't know where it would lie in the middle.
Okay. I have another question. You talk about a finite number of lines. but there should be some uniform. I mean, you should be able to link this number of lines with the height. What kind of link do you have?
Yeah, so if the zeros between t and so I guess the key thing is some sort of separation in the real parts. So if the zeros may be between t and t plus t to the 1/2, if the real parts, the projections of the real parts are either very close to one another or separated by maybe log t squared over log t, then the argument would work. So we could deal with log t divided by log t squared different vertical lines when you're looking between maybe t and t plus t to the 1/2 or something. So, I mean, that's really quite a lot of different vertical lines, I guess.
Yes. That's extremely sharp. I don't know whether someone has other questions.
Yeah, I have a quick question if I may ask.
Please.
Yeah, so my question is related to what Professor Rudnick was asking. So how close to the critical line we can go?
So again, this is, okay. So in principle, as soon as you're a distance sort of log t squared divided by log t or something like that, so you'd expect if you're going a distance just a constant divided by log t, then you've basically not moved off the critical line and you're fundamentally still on the critical line. And we just need to go a little bit further than that for these results to start becoming non-trivial. So it's starting to say non-trivial things, maybe when you're log t squared divided by log t away from the critical line. That's the sort of thing that I would guess. Whether these results are doing better in that sort of regime than the much earlier zero density estimates, I'm not sure. So I don't know if these would really be competitive in that regime because there's certainly some losses in our argument. But this is saying something non-trivial, even very close to the half line, is my feeling, although I'd need to check a few of the details.
Yeah, thanks a lot. Thank you.
So let us thank James again, and if we can, and then let's say that in 2 minutes we'll listen to Philippe Michel. So we have a 2 minutes break. Yes. I don't know whether, je sais pas si tu es là, Philippe.
Ah, je suis là.
Parfait. Et on va voir si tu arrives à partager ton écran. Tu es
Ok, yeah, oui.
Tu es en Suisse?
Yes.
Parce que the background is beautiful, but it's not Switzerland.
Yeah, it's Switzerland. It's a lake. It's in front of my house.
Wow.
But it's not now.
Yes. Okay. Just I get a cup of something and I come. Oh, good. It is time. It is time. It is time. Okay, so we can resume, and we are happy to have Philippe Michel, who will talk to us about simultaneous reduction of complex multiplication elliptic curves. Please.
Okay, so thank you all for being here, and thank you very much for this invitation to speak at Balu Fest. This talk is a bit remote from classical analytic number theory, although there will be some L function, but more in the background. And so this is something which occupy myself for some time now. And this is joint work with Meni Aka, Manuel Luthi, Ricardo Menares, and Andreas Wieser. So, oh, okay. What is happening? Okay, so the main player, the key player will be elliptic curves. And I just briefly recall you that an elliptic curve over a field, it's an algebraic curve of genus 1. And at least so it admits it's a plane projective curve, and in characteristic not too small, it admits a relatively simple equation. And with this coefficient G2 and G3, and this is in homogeneous coordinates. And the curve is supposed to be smooth. And being smooth means that the discriminant of the curve is not 0. And then this elliptic curve up to isomorphism is completely determined by its J invariant, which can be computed from the coefficient of the plane equation. Also, I recall that an elliptic curve is the structure of an algebraic group, commutative algebraic group. And if you take the embedding of the curve in the projective plane, the group law is given by the usual chord and tangent construction. And the zero element of the group is the point at infinity. So if you take this point to be the zero element, so then the addition of 2 points, P and Q, is given by this third point, P plus Q. And you have also a construction how to construct twice a point. Then you take the tangent to the point. You are willing to double, and it intersects the curve into a point which is the opposite, minus 2p, and then you take the symmetry, and you get 2p. So an important invariant of the curve is its ring of endomorphism. So in the beginning, the ring of endomorphism of an elliptic curve is just the set of algebraic maps of the curve to itself, which map the zero element to itself. And if you have this, automatically such algebraic maps are a group morphism. And the set of all such maps has a structure of a commutative ring for composition and addition on the curve. And then you have 3 possibilities basically for the structure of this ring of endomorphism. So either this is just isomorphic to the integers. It's just multiplication of a point by an integer n. Another possibility is that the elliptic curve, this ring of endomorphism is bigger than z, and then it will be, in fact, an order in an imaginary quadratic field. So this is the way I will write such order. So OD is Z plus the ring of integer of an imaginary quadratic field multiplied by D over the fundamental discriminant, and this will be the imaginary quadratic order of discriminant D. And so the discriminant completely determine the quadratic order up to isomorphism. And there is a third, so then this ring of endomorphism is a bit bigger. It is the module of rank 2. And then there is a third possibility, which is that this ring of endomorphism is the module of rank 4. Namely, it is isomorphic to a maximal order in the unique quaternion algebra defined over the rational, which is ramified at some prime p, and which is definite. And in this case, the curve is called supersingular, and automatically the characteristic of the field is the prime p, and one knows that the curve is even it's a priori it comes from a field of characteristic p, it can be defined over fp square, meaning that you can find a plane equation of the curve with coefficient in the finite field fp square. So now I will be more, I will go back to something maybe more elementary. So if the field is at zero characteristic and contained in the complex numbers, then it is well known that the complex point of the elliptic curve form a Riemann surface, and more precisely, it is a one-dimensional torus that is the quotient of C by lattice into C, so rank 2 Z module into C. And so this isomorphism between the algebraic elliptic curve of the complex point and the torus is given in terms of Weierstrass P function, of the Weierstrass P function associated with the lattice. So you take the P function of the lattice, its derivative, and then if you take the congruous class of a complex number modulo the lattice, then you associate to it an algebraic point on the algebraic elliptic curve with coordinate p and p prime, where p is the usual function constructed by averaging over the lattice. And if you make this identification with a torus, the ring of endomorphism of the curve, it's naturally identified with the ring of endomorphism of the lattice, which are the complex numbers which preserve the lattice under multiplication. Okay, so, and then in the complex case, the situation is very simple and elementary. And so now I want to speak of elliptic curves with complex multiplication. So I assume that my elliptic curve has a bigger ring of endomorphism. So, and I will say it is Cm. So in that case, the ring of endomorphism is necessarily an imaginary quadratic order. And so I assume the order is the order of discriminant D. And so an examples of such elliptic curve with complex multiplication is you give yourself a imaginary quadratic field. Inside this imaginary quadratic field, you take a fractional proper ideal with respect to this quadratic order OD. So this fractional ideal is a lattice in C via this embedding. And then your elliptic curve, its complex point, is the quotient of C by this ideal. And then automatically the ring of endomorphism of the curve is exactly the quadratic order. And in fact, this example is best possible. So conversely, an elliptic curve with complex multiplication by an imaginary quadratic order is always of that shape. And so now I will denote by LCMD the set of all elliptic curves over the complex number, which has this quadratic order as endomorphism ring, modulo isomorphism. And then what happens is that the map that we have given, explained here, which to a proper OD ideal associate the complex torus, gives us a bijection between the set of elliptic curves up to isomorphism and the ideal class group of this imaginary quadratic order. Okay. So this is very classical, but okay, maybe I just wanted to recall this. And so now I can, so this will be about equidistribution of this CM elliptic curve, this set of curves. So I will really now discuss the most famous such equidistribution theorem, which is due to Bill Duke. So now, if you consider the set of all complex elliptic curves, then it is well known that this set of elliptic curve up to isomorphism is in bijection with the modular surface of level 1, so H modulo SL2Z. So via this map to say you take an element in the upper half space, and to this element you associate the rank 2 lattice generated by 1 and this element tau. You take the quotient of C by this lattice and you get an elliptic curve, and all are of that shape. And then the SL2Z is to address the question of choosing a basis for this lattice. And under this bijection between elliptic curves and the modular surface, the CM elliptic curves with complex multiplication by OD correspond to the classes of the points whose complex of the point in the upper half plane, so the coordinates are given by say expression of the discriminant D by the discriminant quadratic form. So you take a triple of integers such that B squared minus 4AC equal D. You, out of it, you cook this complex number in the upper half plane. So the roots of the natural polynomial associated to this triple. And it gives, and this gives you a bijection between the CM elliptic curve by OD and this set of complex points, or points on the modular surface. And the theorem of Duke is that as the discriminant goes to infinity among imaginary quadratic discriminant, this set of say CM elliptic curves becomes equidistributed on the modular surface with respect to the usual hyperbolic measure. So here is, so this is the definition of equidistribution, that the Riemann sum associated to this finite set of points converge to the integral of the function. against the hyperbolic measure. And here is a picture of elliptic curves with complex multiplication by this discriminant, and which seems to fill the modular surface according to the hyperbolic measure. You have more points in the bottom and less points on the top, near the cusp. Okay. So now I will speak about something a bit more exotic, or so slightly more exotic, not too much yet, but so if you give yourself elliptic curve with complex multiplication, say defined over the complex number, then what it's possible to prove, who is it? Maybe this is Kronecker, is that the J invariant of your curve is in fact an algebraic number. And because the J invariant is algebraic, the elliptic curve is defined over some number field, which I will write HD, which is the field generated by the quadratic extension of underlying the complex multiplication and the value of the J invariant. So it means that your elliptic curve, in concrete terms, admits a polynomial equation in which the coefficient belong both to this number field. And also what you know is that the extension, this number field, so which is called the ring class field of the order OD, it's Galois over K, over the quadratic extension, and the Galois group is isomorphic to the ideal class group. And these results, they predate the general development of class field theory. Okay. And in fact, there is more. Not only the J invariant is an algebraic number, but in fact, it's an algebraic integer. And it means that essentially, or you can manage more or less to make sure that these coefficients, G2 and G3, are also algebraic integer belonging to this field. And it means that your elliptic curve, whose coefficients are algebraic integers, you can reduce it modulo prime ideal in the number field. And in fact, you may need to make a small extension, but basically you have an elliptic curve whose reduction modulo any prime will also be an elliptic curve, a true elliptic curve over suitable finite field, the residue field. And okay. And what you know is that, okay, so now I will take P rational prime, and then I will choose in algebraic closure of Q, I will choose a place which is above P, which means I will choose consistently for any number field an ideal which lies above P. So this is what it means to choose a place in Q bar above P. And then I can, in particular, I have chosen a prime ideal in this number field. And then I can use this prime ideal to reduce this elliptic curve, since it has coefficients in the ring of algebraic integer of this number field. So if the prime P is inert or ramified in the quadratic field, okay, the quadratic field containing the quadratic order, then the reduction modulo P of the curve is a supersingular elliptic curve. So I recall you, it means that its ring of endomorphism is really big, is as big as possible. It's the maximal order inside quaternion algebra. Okay. Oh yeah, I said maybe in the beginning that the ring of endomorphism is commutative. No, it's not, especially in this case. Okay. So then I can introduce a new type of equidistribution statement. So now I take this prime and I consider the set of all supersingular elliptic curves. And I know they are defined over Fp squared, so I take them over an algebraic closure of Fp, modulo isomorphism, but I could take Fp squared. And now I have my place of reduction to do a reduction mode P. So, and if I assume again that P is inert and ramified in the quadratic field, then you get a reduction mode P map. So it should be read with fracture P, but I just write it red P to simplify, which to your CM elliptic curve associate its reduction modulo fracture P, which will be a supersingular elliptic curve. And so this reduction mode P map, it comes with, so the most concrete way to see it is that if you look at the J invariant of your CM elliptic curve, so it's an algebraic integer, then its reduction modulo P is the J invariant of the of its reduction, so which is a supersingular. And in addition, so this reduction mode P map, it induces an embedding of the ring of endomorphism, which I recall is a quadratic order, inside the ring of endomorphism of the reduced curve, which is a maximal order in quaternion algebra. So now what happens is that this set of supersingular elliptic curve, this is a finite set, and its size, it's approximately P over 12. So what you can look at is you take all the CM elliptic curves, and you want to know, does the reduction mode P map cover the full space of supersingular elliptic curve at P? And if it covers the full space, what are the frequency of a given supersingular elliptic curve being the reduction of CM elliptic curve? And so you have an analog, a mode P analog of Duke's theorem. So which here is a consequence, it go back to another work of Duke and Schultz-Pillow, but it was not phrased in that way. So it was phrased in that way by myself and Elkis, Ono, and Yang. So let's take imaginary quadratic discriminant, assume they are coprime with P, and that you choose your discriminant so that P is inert in the underlying quadratic field. Then the multiset of reduction modulo P of this CM elliptic curve with CM by OD, or CM elliptic curve of discriminant D, become equidistributed on the full space of supersingular elliptic curves with respect to an explicit measure. So it is a probability measure, and basically it assigns to each supersingular elliptic curve a mass which is proportional with the inverse of the group of units of its ring of endomorphism, of, if you prefer, the inverse of the size of the group of automorphism of the supersingular elliptic curve. So this measure, it's not the uniform measure on the finite set, it's not very far from being uniform, but then it's a measure which gives a positive mass to any supersingular elliptic curve. And so what equidistribution means, it means that if you look at the frequency of a CM elliptic curve with a given supersingular reduction, this frequency converges to the mass of this supersingular curve, as defined here. Okay, so in particular, the reduction modulo P map, which is here, it is surjective as soon as D is sufficiently large. Okay, and now what I want to explain is kind of multiply this theorem. Or so what I do now is I consider a finite set of prime, S prime, P1 to PS, and I will only consider discriminants such that all these primes are inert in the quadratic field. So if all these primes are inert in the quadratic field of complex multiplication, then you have a multi-reduction map. So to CM elliptic curves, you associate its reduction modulo P1, its reduction modulo P2, its reduction modulo PS. You can also associate its complex point in the upper half on the modular surface. And so to such a CM elliptic curve, you associate a tuple in the product of the modular surface and the product of all the spaces of supersingular elliptic curves modulo all these distinct primes. And so here is a conjecture, is that, okay, if D goes to infinity, satisfying, so is a sequence of imaginary quadratic discriminant satisfying this assumption and going to infinity, then the multi-reduction multiset is equidistributed on the product of this probability space with respect to the product of the measures, of all the measures that have been defined. So the hyperbolic measures and the measure introduced for the set of supersingular elliptic curves. So, and here is a concrete consequence of this conjecture, is that if you give yourself a tuple of supersingular J invariant, so invariant of supersingular elliptic curves, modulo the various primes, then if you have a discriminant which is large enough, satisfying the above assumptions, then you can find a positive proportion of CM elliptic curves such that the J invariant of in any of these elliptic curves is congruent to the given supersingular J invariant. So it's a kind of asymptotic Chinese remainder theorem for J invariant of CM elliptic curves. Okay? So this is a conjecture, and so this conjecture, it has been proven in some case. So the first case is due to Christophe Cornu. So, and it says the conjecture is true if you look at a sequence of particular discriminant. So you take the quadratic, imaginary quadratic discriminant, which are of the shape fundamental discriminant time power of a fixed prime, and then you take very high power of this fixed prime. So you take all discriminant of that shape. They are not at all fundamental. In fact, they are less and less fundamental as the exponent grows, the n here. And so again, the quadratic field is fixed, and the prime P is fixed, and we assume that, of course, okay, P P, maybe I should have called it Q. No, okay. P, it's not one of the PIs. It's distinct. In fact, it's co-prime with any of them. And then you let the exponent go to infinity. And you have the conjecture is true. So you have multiple equidistribution for the reduction modulo the various prime PIs. And so the proof by Christophe Cornu, in fact, it was inspired by an earlier work of Vinayak Vatsal. And the proof used ergodic methods from ergodic theory, and in particular, it used the work of Marina Ratner on the classification of joinings for unipotent flows on locally homogeneous spaces. So it does not use, And what I want to explain is now another theorem, so which we proved maybe a year ago or a bit more with Meni Aka, Manuel Luthi, and Andreas Wieser. So for this, you fix two extra primes, Q1 and Q2, distinct from the PIs. And then the theorem is that the equidistribution conjecture holds if you consider the subsequence of discriminant satisfying the condition mentioned before, and two additional conditions that the quadratic field Q square root of D is split these two fixed prime Q1 and Q2. So here, the discriminant D can be fundamental or can be anything, but we ask that the quadratic field of this discriminant, which can be varying, always split these two fixed primes. And so this condition that these two primes split in the quadratic field, it's a congruence condition on the underlying fundamental discriminant. So I ask that the Kronecker symbols of this discriminant against Q1 and Q2 are both equal to 1. And this congruence condition, it's called the congruence condition of Linux type. And I will go back to it a bit later. And so here, again, as for the case of Cornu, the proof use methods from ergodic theory, but this time it uses a much more recent result due to Einsiedler and Lindenstrauss. So it's more powerful than Ratner theorem, or it contains Ratner theorem mentioned before, but it allows you to consider a discriminant for which the quadratic field could be varying. Okay. Is there a question? Is there a, at least I don't see questions. No question? Okay. So, and I want to explain also another result. So this is a theorem, and I want also there is another theorem in that direction of this conjecture, which is due to Valentin Blomer and Farrell Brumley. And so who have another result in that direction. So they don't use or they don't need this splitting hypothesis at two primes Q1 and Q2, but so there is a trading. So if you assume a suitable generalized Riemann hypothesis, but a very natural one, I mean no crazy thing like, I don't know, linear independence of zeros or things like this, really the most basic generalized Riemann hypothesis you can imagine for suitable L functions. Then they prove that the conjecture is true, at least when you have two factors. So either you have infinity, so the product of the modular surface and a copy of a super singular set of super singular elliptic curves, or two sets of super singular elliptic curves at two distinct primes. So okay. So one needs, so the proof is very different from this one, really complex. And in fact, it's much more in line with the topic of this conference, because it's heavily used L functions and deeply in a very delicate way. Okay. Okay. So maybe I will just give a quick idea of the proof, of the various ways to approach this method. So one approach is the original approach of Bill Duke. It's based on the use of theta functions. So what you want to do, or what it amounts to do in the end, proving this theorem, is you have a ternary quadratic space. So let G denote this the orthogonal group of this quadratic space. Inside this quadratic space, you give yourself a lattice on which the quadratic form is integral. And then what you need to study to prove these results in the end is to study the set of primitive representation of this quadratic form. For D, it will be related to the discriminant. So this representation, these are elements of this lattice such that the quadratic form take value this integer are D. We ask the representations to be primitive, which is this condition written here, basically that the coordinate of this element are coprime. And then you have this set of representation, which you need to prove is non-empty, but assume you can do it. Then what you have is you take this set of representation is acted on by the integral isometry, so the one preserving the lattice. And then you take the set of classes of such representations. And what you want to show is that this set of classes of representation equidistribute on a set of classes of along a certain ellipsoid associated with Q. So in the case of Duke, so this is what you need to do in general. So this is not specific to theta functions. So for instance, in the case of Duke's theorem, original theorem for so-called Wegner points, then your quadratic space is the space of trace 0 2 by 2 matrices. The quadratic form is minus the determinant. The lattice you are interested in is essentially the trace 0 integral matrices, slightly modified at 2. And then you want to prove that this set of representation equidistribute on this quotient, but this quotient is naturally identified with the modular surface. And then to prove this, Duke used correspondence due to mass to relate the Weil sum that you want to evaluate to Fourier coefficients of modular form of mass forms of half integral weight. And for this, in fact, he was generalizing a previous bound of Iwaniec, previous non-trivial bound for Iwaniec. So here is a picture of an equidistribution. So here I have represented really the ellipsoid. So it's, you see, this sheet of this hyperboloid, it's, you can see it as imagine as modular, as the upper half plane. And this triangle on which you have a lot of points sitting, this is the fundamental domain for the modular surface. Okay, and in the case of reduction modulo P, then the lattice, so then the ternary space, okay, made a mistake, there should be a 0. The ternary quadratic space is the space of quaternions in this quaternion algebra, which are of trace 0, so there should be a 0 here. Oh no, I cannot do it, okay. And then the orthogonal group is the projective group of quaternion, and here is the same lattice. You just replace the integral matrices by this maximal order. And in fact, in that case, not only you need to have something complete, not only you need to represent, to look at the representation inside the lattice L, but you need to look at the representation inside all the lattices which are in the genus class of L. And these genus classes of the lattice L, in fact, they are in bijection with the set of supersingular elliptic curves. Okay. And okay, and then you have the same kind of methods. So you interpret the Weil sum of the problem as a coefficient of half integral modular form, but this time they are holomorphic, and the bound in some cases was given by Iwaniec, and it was Iwaniec's bound was again extended by Duke and also by Fomenko and Golubeva independently. Okay. Okay. Maybe so now I want to pass to the equidistribution, and what I want to say is that to prove multi equidistribution, so for instance for reduction modulo various primes, you cannot use this method based on theta function. They are a bit too coarse. And instead, you have to go back to the work of Gauss and use a more say, dynamical or group theoretic interpretation to the problem. So let's go back to the case of complex elliptic curves. And suppose you have CM elliptic curves, but now represented via its lattice in the complex plane. And then what happens is that you have your lattice. Now take an ideal with respect to this order, a fractional ideal. So it sits into the complex number, and then you form the lattice, which is the product of your lattice lambda and this lattice ideal A. And what you find is that this lattice, it has the same property of being, of having its ring of endomorphism equal to your imaginary quadratic ring, quadratic order. And therefore, out of this lattice lambda and out of this ideal A, you have constructed a new elliptic curve with complex multiplication by the same order. So what happens is that in that way, you have defined, and in fact, this elliptic curve up to isomorphism, it only depends on the class of the ideal class of A. So what you have defined, or what Gauss, in fact, had defined in the different language, it's an action of the ideal class group on the set of CM elliptic curves. And basically, what is happening is that the set of elliptic curves with complex multiplication by OD, it's a principal homogeneous space under the action of the ideal class group. And this action is exactly given by what I have described. So, so then you see, it's more than just looking coarsely at all the representations or all the set of these points, of this say, CM elliptic curve as a global set. Not only, but this set is endowed with a structure because it's acted simply transitively by a group, by this ID class group. And so what you can do now is that if you have this description, in fact, the multiset of the complex elliptic curves or the multiset of their reduction modulo prime have also a group theoretic interpretation. So unfortunately, I would say the most, what I find the most convenient language to transmit this is to become adelic. So I will just briefly go over it. So then your space are identified with adelic quotient, the one on which you want to equidistribute. These are adelic quotient. And the element, so your set of reduction of elliptic curves are inside this adelic quotient are in fact orbits, adelic orbits under the action of a subgroup of the adelic quotient. So this subgroup, the algebraic subgroup involved is the torus associated with the quadratic extension K. So the restriction of scalar of K to Q of the multiplicative group. And then your multiset is really realized as an orbit under the action of this adelic torus. And okay, I will pass on this. Yeah, then so what happens? I will also pass on this. So then now I will explain what is going on. Now, suppose I take my product of super singular elliptic curves. I realize it as an adelic quotient formed as a product associated to the product of adelic quotients. Then now, if I give myself one super singular elliptic curves and with its few reduction modulo the primes, it gives me an embedding of this single one-dimensional torus inside the product of these algebraic groups. And therefore, I have a diagonal torus orbit inside my product, a diagonal adelic torus orbit inside my product of adelic quotient. And and then what is very nice is that the action of the torus, which comes from the action of the ideal class group, is really compatible with this product structure. It means the following. It means that if I take an elliptic curve and I translate it by an element of this torus, think of an ideal in the ideal class group, then when I look at the reduction modulo P of this of the various reduction modulo P of this new elliptic curves, what you see is that these are the reduction modulo P, the translate by the same element T of the reduction modulo P of the initial elliptic curve E. And this is not completely obvious. It comes from an arithmetic version of this action of the ideal class group on the set of CM elliptic curves, which is called the A transform of Serre. So, and this is really a crucial relation that you need to make sure that this torus orbit represent exactly the sequence of multi-reductions. Okay, and now that you are here, then we are here, then what you get from all this interpretation is that all these diagonal torus orbits, so this all these orbits inside this space, so they support a probability measure, and for each discriminant, you have a sequence of probability measures. And so what you want to know is what is the limit of this sequence of probability measures. And the goal is to show that this limit is the full measure on this adelic quotient. And it is at this, so what you know initially is that whenever you project this measure onto any factor on this product, then the projection has a limit, and the limit is a full measure on each factor. This is a consequence of Duke's theorem. So you have this information that you have a measure on the product whose limit project to the full measure on each factor. And then you would like to have a result in the shape of Gursa lemma. So to tell you that in that case, the limit on the product should be the full measure of the product space. And this is true. This you can prove using ergodic method if you assume this splitting condition that I have mentioned on the quadratic field, because the consequence of this splitting condition is that this measure that you have constructed will be measured invariant under the action of two diagonal matrices at these 2' Q1 and Q2. And due to a powerful theorem of Einsiedler-Lindenstrauss, this implies essentially that the limit measure is the full measure. So it's not exactly this, but then you have to do something which, by comparison with their theorem, is much more elementary. And then you conclude the proof. And then so far I did not discuss joint work with Ricardo Menares, so I will quickly do this. And so recently, Sebastián Herrero, Ricardo Menares, and Juan Rivera Letellier have really considerably refined the mod P equidistribution theorem into a p-adic equidistribution statement. And even so, the statement is not the statement of their theorem is not obvious. Because in that case, you don't have an obvious limiting measure. In fact, you have many possible limiting measures. So what happens is that associated to each p-adic discriminant, so a discriminant now of a quadratic extension of QP, or of an order in a quadratic extension of QP, you associate measure on a space which is indexed by the various supersingular elliptic curves, which is a p-adic disk of radius 1. So these p-adic disks, they parameterize deformation of the formal group of attached to the supersingular elliptic curve. And in that shape, if you do this, your reduction modulo P map gets refined into a map from the CM elliptic curve to the union of these p-adic disks indexed by the supersingular curves. And now, whenever you give yourself a p-adic discriminant, you associate to this p-adic discriminant a subspace, and on this subspace, a probability measure, and this subspace is a strict subspace of this union of disk, and which will be the so this subspace, it will be the natural receptacle for the reduction mode P map if the discriminant satisfies, the global discriminant satisfies suitable congruence condition modulo P. And you have one different measure for each case. But so what they could prove is that once you have made all this definition, if you take a sequence of discriminant satisfying, so which is what I call this local congruence condition, then the image of the reduction modulo P map equidistribute according to this measure. So their proof used really the theta function approach, and it's not suitable. Now you would like to do the same with several primes. And so again, you have to go to the group theoretic framework or the adelic framework. So then, we have the following theorem, which we expect, which is the natural multi-prime version of the theorem of Herrero, Menares, and Rivera-Letellier. So now we also with Ricardo Menares. So and so far we are. So this is what we expect. I think we are very close to finish it. But at least for the moment, we can prove at least an important special case of it. And so just here is a corollary, and I will finish here. So suppose you give yourself your S primes, and for each prime you give yourself CM elliptic curves whose discriminant is coprime with pi, and in which pi is inert. And then you give yourself a sequence of imaginary quadratic discriminants, D. And then you have this condition of Q1, Q2, which should not be necessary, but which you have. Then what you can look at is the number of elliptic curves whose J invariant is congruent to this prescribed global J invariant, but modulo P I to the V, and V you take it as large as you wish, but fixed. Then the number of this elliptic curve is is a positive density of the total number of CM elliptic curves. Okay, so I am over time. And so I will just finish here and then wish Balu happy 70th birthday.
Okay, thank you, Michel, for this nice talk. We can clap if you can unmute. Okay, so questions, please. So you can unmute yourself and ask question directly.
Philippe, the last slide, yeah, this last equation, some ways looks a bit like a Gros-Zagier type result.
Yeah, it is in Gros-Zagier. So you absolutely. So you of course there is so in Gros-Zagier, I think they take only one prime. You see, so here in the Gros-Zagier Krell paper, you mean, I guess?
Yeah, singular moduli, yeah.
Ah, exactly. So they prove this. So I don't remember exactly what they prove, but they have something like this. And I think it's only, do they take arbitrary V? I don't exactly remember.
Well, no, they get the full factorization of, well, the difference maybe of norm, maybe not of the individual ones, but there's no difference.
So the factor, when they take two CM elliptic curves, maybe of the same imaginary order, or something like this.
No, I think it's different. I think they are different orders you can do.
Okay. So I have to just to remember to I will. So of course it's closely related. Here, what you have is that it's first it's numerical in the sense that you know with which frequency you have this condition, and also you have a handle on. So you fix yourself the various primes. So I guess you have the factorization, so you have a control on the shape of this factorization modulo multiple primes. Okay, I would have to re-look at what they did. No, but it's closely related. And it's also closely related with the paper of Elkis, Yangono, and yeah.
Yeah, I think they have different objectives, Kurosagi, but I'm just wondering if you might be able to give more precise versions of their results or something.
It's possible. Maybe, so I would imagine that this congruence is a form of a more precise version. But okay, I will look and I will tell you exactly what it is, if and how much more precise it is.
Great, thank you.
Okay, then we can thank Michel again. Philippe again, sorry. It seems that Ram has some difficulty to log in, so we'll continue in 10 minutes. Say at
I was able to log in, so I'm here.
Oh, finally. Oh, good. So let's say that we start in 2 minutes, yeah? Let's say we start at, yeah, I don't know the time according to the country, but let's say in 2 minutes, so that people can get a cup of coffee and come to listen to you, yes?
Did you want me to share my screen now, or?
That would be a safe thing to do, yes. To start to see whether it works, yes.
If you will know what are you talking on.
Pardon me?
At least you will know what are you talking on. At least the title of your talk.
Yes.
Oh yeah. Oh yeah, yes.
Perfect.
Hi, Balu.
Hi.
Happy 70th birthday.
So we'll resume in 2 minutes and I get a cup of coffee.
Okay.
So, two minutes are done. Yeah, I see that everyone seems to be here. So we'll resume, yes. We are happy to listen to Ramurti who is in Canada, I guess, and who will speak about the normal number of prime divisors of arithmetical function at shift of prime arguments. Please.
Okay, thank you, Olivier. I'm very happy to be part of the Balu 70th birthday celebrations. Our associations go a long way back to his days when he was a graduate student and when I was a graduate student. So it's really a privilege to be speaking at this conference. So let me begin with the motivating theorem of 1916. Hardy and Ramanujan wrote a beautiful paper on the number of distinct prime divisors of a natural number. They showed that if you look at any fix an epsilon positive, the number of m less than or equal to n for which omega of m minus log m deviates from, omega of m deviates from log m by a square root log m. That's very rare, and a random number m usually has about log m distinct prime divisors in this sense. So this is a beautiful paper. It's almost a century old now. So there's G.H. Hardy, and there's Ramanujan. And this particular paper is full of many ideas, and it's essentially spawned the development of probabilistic number theory in a variety of ways. Unfortunately, I won't have time to go into the historical evolution of this subject, but certainly this paper has foundational roots. So let's see why you would expect a theorem of this sort. So the number of m less than n, which are divisible by a given number d, is about n over d, with an error of about 0.1. And so the probability that a random number is divisible by d is usually 1 over d. So if we want to count the number of prime divisors it has, we would expect for every prime p, the probability of p dividing a number would be 1 over p, and then you would sum over all the possible prime divisors less than n. And so you get summation 1 over p as a probability. And by a famous theorem of Merton, this is asymptotic to log n. So this is the intuition that would suggest the Hardy-Ramanujan theorem. And now it's fortunately, all the ingredients are in place to give a rigorous proof of this fact. So in general, what we can apply this philosophy to say that any random number should have log n prime divisors, unless it's of course a special shape. So a prime number, for example, you wouldn't expect it to be a random number because a prime number is a special number. But if I took a prime number and I shifted it by 1, let's say p plus 1 or p plus 2, you'd expect that to be random, and therefore you'd expect the number of prime factors of p plus 1 or p plus 2 or p plus a in general to be about log p. So that's the philosophy behind this. So in the following, we'll expect shifts of primes such as p plus a to behave randomly when a is not 0. And so we expect it to have log p prime factors. And from this perspective, you can now take any arithmetical function and you could look at the arithmetical function and look at it at prime arguments and shift it by a non-zero, and then if it has good chance to be random behavior, you'd expect log of the function to be the normal number of prime factors. So that's philosophy underlying much of what we're going to talk about. This is actually, in the case of shifts of primes, it's actually borne out by a famous theorem of Halberstam. In fact, I believe it was Halberstam's PhD thesis, the idea that p plus a has usually log p prime factors. So after the paper of Ramanujan and Hardy was published in 1917, about 20 years after that, Paul Turan came up with a very beautiful and simple, elegant proof, essentially a 2-page paper, in which he showed their result can be deduced in a very simple sort of way. And it's interesting that Mark Katz was stimulated by reading Paul Turan's paper and prodded him several times actually to see if he can extend his argument to study so-called higher moments. Turan replied that he didn't have any application or any reason for that, and so it never did it. So it was left to Erdős and Katz actually to carry the program out. And that's the famous 1940 theorem, in which they showed that omega of n minus log n over square root log n is normally distributed. So here phi is the normal distribution. That's an amazing theorem. It's a beautiful theorem. And this is usually considered the beginning of probabilistic number theory. So it's a beautiful episode in mathematics, and the proof of their theorem makes elaborate use of Brunn's sieve. Now, interestingly enough, over the decades. Many mathematicians have contributed to the development of probabilistic number theory. And in particular, I want to focus on a beautiful paper of Billingsley, in which he tries to use essentially the central limit theorem to deduce this result, and thereby dispensing with the use of the sieve, essentially, or minimizing the use of the sieve, let's put it that way, minimizing the use of the sieve in this particular thing. And of course, Billingsley was focusing on the Erdős-Katz, the classical Erdős-Katz theorem. And in that sense, he did succeed in eliminating the use of the sieve by invoking the central limit theorem. But for the applications we have in mind in this particular talk, the use of the sieve is axiomatized, and so we want to focus on that. So here's the axiomatic framework. We consider a sequence of numbers, A sub m's, defined on a particular subset S of the natural numbers. So think of capital S to be, let's say, prime numbers. And so A sub m could be a sequence indexed by prime numbers. For example, we could take A sub p to be tau of p, the Ramanujan tau function. And so we may be interested in how many prime factors that the Ramanujan tau function would typically have. So in that kind of, with that prototypical example, let's proceed and axiomatize the whole thing. So let S of n be the number of m less than n, which are n in S. And we will assume that there's a polynomial growth for the sequence. And that for each natural number d, Sn d will be the number of m less than or equal to n, such that A sub m is divisible by d. And so we need to postulate, just as you would in sieve theory, postulate some sort of distribution result. So Snd would be the number of, we expect the density delta of d times S of n plus a small error. So we'll assume that. And then we assume something about the density here. We will assume that the lim sup of that is less than 1. And typically, delta of d would be 1 over d, typically. It doesn't have to be exactly 1 over d. It could be asymptotic to 1 over d. And we just like to have the lim sup of this thing is less than 1. This is just really essentially a technical condition. It'll show up later why it's essential. But then now we postulate that Snd is usually delta of d with a very small error. This looks like a Bombiri-Vinogradov style theorem for this arbitrary sequence, but it's much weaker, as you will see, because as I said, delta of L is usually 1 over L, and these are primes. And so here, mu sub n is log alpha sub n. So typically alpha sub n is going to be some small power of n. So that essentially mu sub n is going to be log n. And therefore, from a standpoint of the Bombiri-Vinogradov theorem, this is much weaker because we're only asking for a saving of a power of log n. And usually, typically in the Bombiri-Vinogradov style theorems, you want savings of arbitrary powers of logarithms. So this is much weaker. And so these are the basic axioms, basic axiomatic framework in which we want to study these problems. So a couple of months ago, in joint work with Kumar Murthy and Sudhir Pujari, we proved what we called an all-purpose Erdős-Katz theorem. So you assume that with those axioms in place, which are very mild axioms, with this kind of a Bombiri-Vinogradov style, weak Bombiri-Vinogradov style theorem in place, immediately you get an Erdős-Katz style theorem for the number of prime divisors of A sub n. It usually is log n minus, divided by root log n. And so you get this phi, and L is prime, and phi is, of course, the normal distribution, and this probability P sub n S is the measure that you would assign to the set S sitting inside 1n, which assigns the measure 1 over Sn to each point. So that's, and then you take a limit of these probabilities. So
then you
here,
mean minus un, Ram.
Pardon me?
You mean minus the mean.
Oh yeah. You're absolutely right. Yeah. So I think I stated this. Later on, it'll be exactly what you just said. it'll be minus mu sub n divided by the stand. Thank you very much. Yeah. So that's the general, you're absolutely right. So here's the general theorem. Sorry, I think I cut out wrong part of the slide and pasted it. This is the defects of technology here. Okay, so we have exactly that. And so the axiom allows us to, the technical axiom, if you remember, on that lim sup delta L being less than 1, is to allow that this kind of inequality to hold. And the interesting thing is actually omega is the number of distinct prime divisors, and capital omega would be the number of prime divisors counted with multiplicity. And the advantage of looking at capital omega versus little omega is that capital omega is completely additive. And so this saves us a lot of trouble, actually. Technical difficulties are eliminated. So it would be convenient to move from this to capital omega, and you just need one more axiom that it doesn't deviate too much. And once you axiomatize that way, you actually get a theorem with capital omega in place. So we need one more small condition about the convergence of the squares don't contribute too much to this sequence. So this is basically the axiomatic framework behind. So there are a couple of corollaries of the all-purpose theorem. Of course, the classical Erdős-Katz follows immediately. If you have any irreducible polynomial with neutral coefficients, then you can get an Erdős-Katz law for that. Then you get Halberstam's theorem, who first studied omega of shifts of primes. So it satisfies an Erdős-Katz law. And then there's a famous theorem, well, a theorem, I'm not sure if it's famous, but anyway, it's a theorem that we proved with Philip Sidak, that if A is a natural number greater than 1, f sub A of P is the order of A mod P, then f sub A of P also behaves very randomly and satisfies an Erdős-Katz law. The only problem here is that we need to assume a quasi-GRH, quasi-generalized Riemann hypothesis, where by the generalized Riemann hypothesis here, we mean that the Artin L series, these non-abelian Artin L series to a certain extension, don't have any zeros to the right of 1 minus epsilon for a fixed epsilon positive. So that is the condition we need. Now, if that condition could be replaced by some sort of Bombiri-Vinogradov style theorem, but we have no clue at the moment as to how to prove some sort of non-abelian versions of the Bombiri-Vinogradov theorem. And then there we have this theorem about an old result of myself and Kumar Murthy, where we studied the Ramanujan tau function, and there again we were interested in finding the normal order of tau p, and showed that it satisfies again Erdős-Katz law. Again, unfortunately, I had to assume the quasi-GRH. Now, the interesting thing in this study of the omega of tau of p, or omega of A of p, where A of p is the p Fourier coefficient of an Hecke eigenform in general, this is facilitated by a famous theorem of Deligne that tells you that you can associate an L-adic representation to a modular form, which allows you to move study of divisibility of sequences of Fourier coefficients of eigenforms into a Chebotarev density theorem, which you can then apply with a good error term and deduce divisibility properties and check that the axiom that we had imposed, the Bombiri-Vinogradov style axiom we had imposed, actually works. And then there's another theorem of Ali Miri, Kumar Murthy, and Yuru Liu. If E is an elliptic curve without complex multiplication, then the number of points on the elliptic curve also has a normal number of prime factors, satisfies an Erdős-Katz law again, modulo quasi-GRH. And if it has CM, then you can remove GRH, because if you have CM, then it means that you can move the divisibility question into primes distribution in a imaginary quadratic field. And fortunately, by theorems of Martin Huxley and Robin Wilson, we have some sort of non-abelian version of the Bombay-Vinogradov theorem for those CM extension, for those imaginary quadratic fields. Sorry, it's an abelian thing because we're talking about imaginary quadratic fields. And we have these theorems which you can use and eliminate the use of the Riemann hypothesis. In very, very recent work with Kumar and Sudhir, we showed that you can now apply this axiomatic framework to study many things like sums of Fourier coefficients of Hecke eigenforms. So if I took, two eigenform coefficients and added them, you'd expect this to be a random number again. And so you'd expect the number of prime factors to be log p again. And so again, this has an Erdős-Katz law. You may be wondering, why would you take sums of Fourier coefficients? Well, it actually happens that supposing I have a curve of genus 2, then the Jacobian of that curve has an L function, which is products of Hecke eigenforms of weight 2. And then if you think about it, the number of points mod p of the Jacobian is essentially given by p plus 1 minus some sums of Fourier coefficients. So it is related to, there is a geometric connection to this study. And so the question you may ask is, well, you're assuming the generalized Riemann hypothesis. Is it possible to get some unconditional results? And the answer is to some extent yes, except that you have to define omega star of n to be the number of prime factors of n which are less than some power of log n. So if I want to count the number of primes of n which are less than some small power of log n, then you can actually eliminate the Riemann hypothesis. And now with the probabilistic intuition, you would expect an extra log, you see. Log of log n to the kappa would be triple log. So you expect some theorem like this, and indeed you can prove this without any hypothesis. And the same is true with all these applications which involve the Chebotarev density theorem. Now I want to talk a little bit about some recent work with my student Arpita Kaur. She graduated and she now works for Bell Canada. So here are some of my collaborators, there's Sudhir, and there's Arpita, and here we are at the Sun Temple in Bhubaneswar, Konarak Sun Temple. So all of my students have Erdős number 2, and they have Balu number 2 as well. So this is the future generation. So what about shifts of prime arguments of arithmetical functions? So here's what we were doing, Arpita and myself, thinking about normal order of the Euler function with shifts of primes. So what we could prove is, we'll take the question in 2 steps. We'll first try and generalize Turan's theorem, which is concerned about the normal order, or the Hardy-Ramanujan theorem. And then we'll try and consider the Erdős-Katz style theorem. So first, the normal order type theorem, these both involve some different ingredients. You expect, again, phi of, so p plus a is random, and all of a sudden phi of p plus a should be more random. And in fact, it does show up. So if you think, I'll give some intuition afterwards, but basically this is saying that the normal number of prime factors of the Euler phi function evaluated with shifts of primes is 1/2 log x squared. And so you can prove this without any hypothesis. And then of course you have the Erdős-Katz law, which will tell you that the situation here is something like 1/2 log x squared with a standard deviation of this, but there's this extra cube root of 3 that shows up. It's kind of an interesting phenomenon. This was already apparent in my earlier work with Kumar on the normal number of prime factors of the tau function. So with suitable normalization, this is saying that this whole thing is normally distributed. So what's the intuition towards the proof of the theorem? Well, the intuition is the following. You have a multiplicative function, let's say, And if I were to take f of p plus a, well, I factor p plus a. So let's factor it into products of prime powers and evaluate it. And we expect that the number of prime factors, so basically the number of factors here is to be like log p. And then we expect f of q to the a to behave randomly. So we expect log p times log p squared, but there's a half that shows up, which is interesting. If you do the intuition correctly, you do get a half. So for prime p, you can factor this into a product of prime powers. And then since phi is a multiplicative function, you can just say phi, that is the product of phis, and then break up the phis into two parts where we look at the contribution coming from small so-called small prime factors and the contribution coming from so-called big prime factors. And so y here is a suitably chosen parameter. And then we want to use the omega function because, as I mentioned before, the advantage of using omega is that it's completely additive as opposed to the little omega function, which is only, what they call it, just additive, I suppose, is the terminology. So because of its complete additivity, it is convenient to use the capital omega function. And so we end up getting capital omega phi of p plus a to be just the sum of the phi omega of these quantities. And then you would then break up this sum into two parts according to small prime powers and big prime powers. And you would also truncate the contribution according as count the primes less than small power and count the primes bigger than small power. And the point is that primes which are big will actually be a bounded number. And so essentially it boils down to studying contributions essentially from small primes. Usually z is going to be a small power of x. And finally, when you interchange this summation, you can see that you're counting primes in arithmetic regressions here. And then, of course, you would use the Bomberi-Vinogradov style idea. You would write down the main term and then the error term and try to exploit the error term here. And so that's basically where the use of the Bomberi-Vinogradov theorem comes in. And so in this particular example, when we're talking about shifts of the Euler phi function at primes, we can use the Bomberi-Vinogradov theorem and not invoke any unconditional Riemann hypothesis. It's not completely straightforward, but it's more or less feasible. I mean, you do have to break it up into pieces. So now, if I want to study the tau function evaluated shift of primes, so let's recall a few facts about the tau function for those of students in the audience. Ramanujan discovered this, well, this goes back to Jacobi actually, but anyway, Ramanujan discovered that this particular function, which is the Ramanujan delta function, has interesting coefficients, namely that these coefficients tau n, given by this infinite product here, were multiplicative. So he made this conjecture. These are three conjectures in a famous paper of Ramanujan in 1916, that it's a multiplicative function, that for prime powers, tau of p to the r satisfies the second order recurrence relation. And finally, the tau of p is bounded by 2 times p to the 11.5. So these were these conjectures that essentially electrified much of the development of both number theory and algebraic geometry in the 20th century. And shortly after Ramanujan made these conjectures, about a year after, I believe, Mordell managed to show the first two conjectures immediately. But it's interesting, it's a curious aspect of history that Mordell seemed to be fixated on the tau function, and unfortunately for him, and perhaps fortunately for Hecke, He didn't see the general pattern, although the pattern was evident in his paper. So it's only 1934, I believe, that Hecke realizes the general theory behind this multiplicativity of these Fourier coefficients. So it had to wait another 20 years before somebody figured out the pattern. So these two conjectures of Ramanujan come immediately as a consequence of a general theory of modular forms. The third conjecture is deeper and really does involve algebraic geometry, as far as I'm aware. I mean, there is, of course, a method via the Langlands program, which uses the symmetric power L functions, but that is more complicated. So in 1984, Kumar and I proved, assuming a quasi-GRH, that you could show that these tau function has log p prime factors. So there's the analog of that. And then here for tau of n, we have a normal order of half log n squared. So these two theorems were, again, you had to use a certain quasi-GRH. A year later, we proved a Erdős-Katz law. So we showed that tau p has an omega tau p has an Erdős-Katz law. And I forgot to state it here, but omega of tau of n also has a Erdős-Katz law. Now, the strategy for shifts of primes is as before. Supposing now, instead of studying tau of p, I wanted to study omega of tau of p plus 1, or omega of tau of p plus 8. How would you do that? So this is analogous to the Euler phi function that we had looked at in the before. So here again, we would try to write our p plus a as a product of prime powers. And because tau is a multiplicative function, tau, this product, will be product of the taus. And then again here, we would break up the tau as contributions from small primes and contributions from big primes. And now, if you're wondering about little omega, you can see there how problems will arise. So it's probably a good idea to shift to capital omega, prove the theorem for capital omega, and then deduce that the little omega and the capital omega really don't deviate very much. So that's basically the strategy for this calculation. So again, we would break it up into small primes and big primes. And capital omega then becomes sum of the omega of these factors. So you can now see these things entering into the picture. And then, as you can guess, if I wanted to take the average order first, I would sum this over p, and I would sum this over p, and on interchanging summation, you would see that I would get coefficients of this type, and then primes p, such that I would write down, the primes in arithmetic progression. So you would actually get primes in arithmetic progressions that you could use. So here, the coefficient is omega of tau of q, and then now when I interchange the summation, you're going to be getting primes in ordinary arithmetic progressions. Then you may say, well, wait a minute, do you really need Bombay-Vinogradov theorem? And the answer is you don't if you were looking at the primes that are coming from the arithmetic progression here. But the coefficient is omega tau of q over, this coefficient is, these are primes here. And so you need to know the asymptotic behavior of omega of tau of q. And for that you need the earlier work that Kumar and I did about almost 40 years ago. So the theorem which shifts, so to make a long story short, the theorem which shifts is basically that if you take the generalized Riemann hypothesis, assume that a quasi-generalized Riemann hypothesis will not do. That's the funny thing. I believe we need the full strength. Then you get that omega of tau of p plus a is half log x squared plus log x to the 3/2 again. It's kind of a Erdős-Katz's law. And this should be compared to the theorem proved earlier with Kumar on the normal order of omega 5n, where no unproved hypothesis was used since we had the Bambier-Vinogradov theorem in that case. So these results signal a future direction toward the analogs of the Bambier-Vinogradov theorem to a non-abelian setting. And so in closing, I want to wish Balu a very happy birthday. The Wheel of Time is majestic, Kalu. A very happy 70th birthday, Balu. So thank you very much.
If you manage to unmute, you can clap. So thank you for this nice talk. Does anyone have some questions? Comments, proofs? So, no. So it seems that we'll simply thank the speakers of this afternoon.
Gérald avait quelque chose.
Yeah, I don't hear
Gérald
so
voulait dire
well.
quelque chose.
I don't hear so well, so.
Hello. Sorry
Yes.
for interrupting, sir. A participant has raised his hand, I think.
Yeah,
Gerald Tenebum. Sorry.
Gerald should ask his question directly because there's things that I don't see.
Olivia, if you go to the participant list, you can see there will be raised hands, so it will be in the.
If anybody has a question, all you need to do
Please unmute yourself.
Unmute and yeah, please.
Okay.
Please,
I can see Gerald's hand is up. I can see that.
So Gerald, please.
So Gerald, you can
ask your
unmute.
question.
Can you hear me?
Yes.
Yes.
Perfectly.
Okay. So just regarding the Erdős-Katz's
Yes.
law for omega of phi of n. So I wanted to mention first a theorem of Erdős and Pomerance, who proved the limit law with the constant 1/√3, and then there is a result of Balazar and Smatty. Let me remind you, that's 1989, which gives a remainder term of 1/√log x, a factor 1/√log x for the remainder term. And then there is a result of myself in the Ramanujan Journal of Math 2017, who provides a general formulation with the same error term, but with weights, with a very large number, possibility for weights, also for the omega of phi of n. So that's, I would just wanted to point out these references. Did you hear me?
Okay, well, thank you. I wasn't aware of the later work. I certainly wasn't aware of the error term, which you are pointing out. That's good. Well, certainly these papers are not written up yet, so we'll certainly put these references in. Thank you.
Well, I can provide the references by mail if you need.
Sorry, I'm muted. So thank you.
Oh yes, please do. That'll be very helpful. Thank you. Yeah, please do that.
Okay, I will write to you. I will write to you.
Okay, so if no further questions, then let's.
I have a question.
Is there somebody else? Somebody?
Yeah.
Oh yeah, thank you. Yeah, somebody else has a question. Arvind Kumar. Yeah, Arvind
Yes.
Kumar, go ahead.
I want to know that why did you assume the weights are 2 only while proving the normal order for the sum of the Fourier coefficients? Can you hear me?
I didn't quite, part of your speech was broken on my end. Could you just repeat? Yeah, could you repeat it again, please? Yes.
Yeah, so you assume that the weight of the modular
Can you
forms are
repeat,
2
please?
while, yeah, so weight of the modular forms are 2 while proving the normal order of the sum of the Fourier coefficient.
Mhm.
So why do we need to restrict for weight 2 only?
Right. Yeah, that's a good question. There are, in considering trying to apply the Chebotaur density theorem, one needs to examine the image of the Galois representation. And in the process of doing that, in the case of weight 2, the image is slightly simpler to analyze. For higher weights, there's a restriction on the determinants, which makes our calculations a little bit more complicated, which we have not done yet. So we have simplified the analysis, because you see with research, it always perhaps proceeds in small steps. And so already, I mean, the whole idea of looking at this thing is an interesting idea. It starts actually with Kumar. But the question of technically analyzing it requires microscopic analysis. If we notice that if the weight increases, the image is getting more complicated to analyze. So we focused our attention on the weight 2 case for the time being. We expect that with a little bit more work, we should be able to analyze for higher weights as well.
Okay. Yeah. Thank you.
Does that answer your question?
Yes, very much. Thank you.
I'm not sure if I'm being heard. Am I coming through?
Yes. Yeah, there is some delay in the conversation. Okay. Yes, okay. I mean, it answers my question. Yes, thank you.
Then there's a question by Sudhir Puchari. Maybe you can please ask your question.
Yeah, can you hear me, sir?
I can. I don't know whether.
Yeah, could you? Yes. I think we lost the connection for a while.
Yeah, can you hear me now?
Yes.
Pardon me?
Yeah, can you hear me?
Oh yes, I can hear you now. Yes.
So in the result with Arpita.
Oh, hello, Sudhir. Yes, I now recognize you, Sudhir. Okay, yes.
Yeah, in the result of yours with Arpita, so if you replace p by some, like, let's say, square free integer, is it possible to obtain similar kind of result?
That's probably a good question. Offhand, I don't know the answer to that, but I think the axiomatic framework will. So the first step is to look at the intuitive reasoning and see what you expect. The second thing is to ignore error terms and see what kind of a dominant term one would expect. And if that kind of comes through, then one should get one's hands dirty and actually deal with those error terms. I would say if you replace the primes with square free numbers, as you say, I suspect that you will be confronting the distribution of square free numbers in arithmetic progressions, for which you have lots of good information. Yeah. And so anytime you have some sort of Bombiri-Vinogradov style theorem for a sequence of numbers, it would come through. Yeah.
Thank you. Thanks a lot. Thanks for the nice talk.
Okay.
Oh, yeah.
So thank you. Did I forget someone else? No, I think I didn't forget anyone. Okay, so now we can thank the speakers of this afternoon. The conference will resume at, in 1 hour and 20 minutes, because I cannot tell you the time. It's 6 hours for us, but it's in 1 hour and
40 minutes.
No,
40
1 hour
minutes.
and 10 minutes, sorry.
No, we meet in 40 minutes, I think.
In 40 minutes, okay. Okay.
Yeah.
So the conference will resume in 40 minutes. And so thank you for the speaker of this session.
Thank you,
Okay.
Olivier. Thank you very much for chairing the session. And in next session, Anirbandha will take over, and Adhikari will be the chair of the next session. So see you there.
Perfect. See you.
Bye.
Bye.
So it's good to see you, Jean-Marc.
Aha, hello. Great talk, thank you.
You're welcome. Your bookshelf and my bookshelf look similar.
Yeah, of course.
Books are easy to organize, but paper is not.
Yeah.
That's good. Okay, so I'll have to say bye because I have to teach actually a course. I'm teaching a class, and I have to get ready for that. So thank you again, Olivier. Okay, bye. Happy birthday, Balu. Yeah.